Aren't they some good looking images? And even better that they're from our own custom dataset. Now we've got one more step. We're going to turn our dataset into a data loader. In other words, we're going to batchify all of our images so they can be used with a model. And I gave you the challenge of trying this out yourself in the last video, so I hope you gave that a go, but let's see what that might look like in here. So I'm going to go 5.4. Let's go, what should we call this? So turn custom loaded images into data loaders. So this is just goes to show that we can write our own custom dataset class and we can still use it with PyTorch's data loader. So let's go from utils, torch.utils, that is, utils.data, import data loader. We'll get that in here. We don't need to do that again, but I'm just doing it for completeness. So we're going to set this to train data loader custom, and I'm going to create an instance of data loader here. And then inside, I'm going to pass the data set, which is going to be train data custom. I'm just going to set a universal parameter here in capitals for batch size equals 32, because we can come down here, we can set the batch size. We're going to set this equal to 32, or in other words, the batch size parameter we set up there. We can set the number of workers here as well. If you set to 0, let's go see what the default is actually. Torch, utils, data, loader. What's the default for number of workers? 0. Okay, beautiful. And recall that number of workers is going to set how many cores load your data with a data loader, and generally higher is better. But you can also experiment with this value and see what value suits your model and your hardware the best. So just keep in mind that number of workers is going to alter how much compute your hardware that you're running your code on uses to load your data. So by default, it's set to 0. And then we're going to shuffle the training data. Wonderful. And let's do the same for the test data loader. We'll create test data loader custom, and I'm going to create a new instance. So let me make a few code cells here of data loader. I'm going to create a data set, or pass in the dataset parameter as the test data custom. So again, these data sets are what we've created using our own custom dataset class. We're going to set the batch size equal to batch size, and let's set the num workers equal to 0. In a previous video, we've also set it to CPU count. You can also set it to 1. You can hard code it to 4. All depends on what hardware you're using. I like to use os.cpu count. And then we're not going to shuffle the test data. False. Beautiful. And let's have a look at what we get here. Train data loader custom and test data loader custom. And actually, I'm just going to reset this. Instead of being OS CPU count, I'm going to put it back to 0, just so we've got it in line with the one above. And of course, num workers, we could also set this num workers equals 0 or os.cpu count. And then we could come down here and set this as num workers and num workers. And let's have a look to see if it works. Oh, beautiful. So we've got two instances of utils.data.dataLoader. Now let's just get a single sample from the train data loader here, just to make sure the image shape and batch size is correct. Get image and label from custom data loader. We want image custom, and I'm going to go label custom equals next, and I'm going to iter over the train data loader custom. And then let's go print out the shapes. We want image custom dot shape and label custom. Do we get a shape here? Beautiful, there we go. So we have shape here of 32 because that is our batch size. Then we have 3 color channels, 64, 64, which is in line with what? Which is in line with our transform that we set all the way up here. Transform, we transform our image. You may want to change that to something different depending on the model you're using, depending on how much data you want to be comprised within your image. Recall, generally a larger image size encodes more information. And this is all coming from our original image folder custom dataset class. So look at us go. And I mean, this is a lot of code here, or a fair bit of code, right? But you could think of this as like you write it once, and then if your data set continues to be in this format, well, you can use this over and over again. So you might put this image folder custom into a helper function file over here, such as dataset.py or something like that. And then you could call it in future code instead of rewriting it all the time. And so that's just exactly what PyTorch has done with torchvision.datasets.image folder. So we've got some shapes here, and if we wanted to change the batch size, what do? We just change it like that. 64. Remember, a good batch size is also a multiple of 8 because that's going to help out computing. And batch size equals 1. We get a batch size equal of 1. Whew, we've been through a fair bit, but we've covered a very important thing, and that is loading your own data with a custom data set. So generally, you will be able to load your own data with an existing data loading function or dataset function from one of the Torch domain libraries, such as Torch Audio, Torch Text, Torch Vision, Torch Rec, and later on when it's out of beta, Torch Data. But if you need to create your own custom one, well, you can subclass torch.utils.data.dataset and then add your own functionality to it. So let's keep pushing forward. Previously, we touched a little bit on transforming data, and you may have heard me say that Torch Vision transforms can be used for data augmentation. And if you haven't, that is what the documentation says here. But data augmentation is manipulating our images in some way, shape, or form so that we can artificially increase the diversity of our training data set. So let's have a look at that more in the next video. I'll see you there. Over the last few videos, we've created functions and classes to load in our own custom data set. And we learned that one of the biggest steps in loading a custom data set is transforming your data, particularly turning your target data into tensors. And we also had a brief look at the Torch Vision transforms module, and we saw that there's a fair few different ways that we can transform our data. And that one of the ways that we can transform our image data is through augmentation. And so if we went into the illustration of transforms, let's have a look at all the different ways we can do it. We've got resize, it's going to change the size of the original image. We've got center crop, which will crop. We've got 5 crop. We've got grayscale. We've got random transforms. We've got Gaussian blur. We've got random rotation, random affine, random crop. We could keep going. And in fact, I'd encourage you to check out all of the different options here. But, oh, there's auto augment. Wonderful. There's random augment. This is what I was hinting at. Data augmentation. Do you notice how the original image gets augmented in different ways here? So it gets artificially changed. So it gets rotated a little here. It gets darkened a little here, or maybe brightened, depending how you look at it. It gets shifted up here, and then the colors kind of change here. And so this process is known as data augmentation, as we've hinted at. And we're going to create another section here, which is number 6, other forms of transforms. And this is data augmentation. So how could you find out about what data augmentation is? Well, you could go here, what is data augmentation? And I'm sure there's going to be plenty of resources here. Wikipedia, there we go. Data augmentation in data analysis are techniques used to increase the amount of data by adding slightly modified copies of already existing data or newly created synthetic data from existing data. So I'm going to write down here, data augmentation is the process of artificially adding diversity to your training data. Now, in the case of image data, this may mean applying various image transformations to the training images. And we saw a whole bunch of those in the Torch Vision transforms package. But now let's have a look at one type of data augmentation in particular, and that is trivial augment. But just to illustrate this, I've got a slide here ready to go. We've got what is data augmentation, and it's looking at the same image but from different perspectives. And we do this, as I said, to artificially increase the diversity of a data set. So if we imagine our original image is over here on the left, and then if we wanted to rotate it, we could apply a rotation transform. And then if we wanted to shift it on the vertical and the horizontal axis, we could apply a shift transform. And if we wanted to zoom in on the image, we could apply a zoom transform. And there are many different types of transforms, as I've got a note here. There are many different kinds of data augmentation, such as cropping, replacing, shearing, and this slide only demonstrates a few, but I'd like to highlight another type of data augmentation, and that is one used to recently train PyTorch Torch Vision image models to state-of-the-art levels. So let's take a look at one particular type of data augmentation used to train PyTorch vision models to state-of-the-art levels. Now, just in case you're not sure why we might do this, we would like to increase the diversity of our training data so that our images become harder for our model to learn, or it gets a chance to view the same image from different perspectives so that when you use your image classification model in practice, it's seen the same sort of images but from many different angles. So hopefully it learns patterns that are generalizable to those different angles. So this practice hopefully results in a model that's more generalizable to unseen data. And so if we go to Torch Vision, state of the art, here we go. So this is a recent blog post by the PyTorch team, how to train state-of-the-art models, which is what we want to do. State-of-the-art means best in the business, otherwise known as SOTA. You might see this acronym quite often. Using Torch Vision's latest primitives. So Torch Vision is the package that we've been using to work with vision data, and Torch Vision has a bunch of primitives, which are, in other words, functions, that help us train really good performing models. So blog post here. And if we jump into this blog post, and if we scroll down, we've got some improvements here. So there's an original ResNet 50 model. ResNet 50 is a common computer vision architecture. So accuracy at 1. So what do we have? Well, let's just say they get a boost in what the previous results were. So if we scroll down, there is a type of data augmentation here. So if we add up all of the improvements that they used, so there's a whole bunch here. Now, as your extra curriculum, I'd encourage you to look at what the improvements are. You're not going to get them all the first go, but that's all right. Blog posts like this come out all the time, and the recipes are continually changing. So even though I'm showing you this now, this may change in the future. So I just scrolled down to see if this table showed us what the previous results were. Doesn't look like it does. Oh no, there's the baseline. So 76, and with all these little additions, it got right up to nearly 81. So nearly a boost of 5% accuracy. And that's pretty good. So what we're going to have a look at is trivial augment. So there's a bunch of different things such as learning rate optimization, training for longer. So these are ways you can improve your model. Random erasing of image data, label smoothing, you can add that as a parameter to your loss functions, such as cross entropy loss, mix up and cut mix, weight decay tuning, fixed res mitigations, exponential moving average, which is EMA, inference resize tuning. So there's a whole bunch of different recipe items here, but we're going to focus on one. We're going to break it down. Let's have a look at trivial augment. So we'll come in here. Let's look at trivial augment. So if we wanted to look at trivial augment, can we find it in here? Oh yes, we can. It's right here. Trivial augment. So as you'll see, if you pass an image into trivial augment, it's going to change it in a few different ways. So if we go into here, let's write that down. So let's see this in action on some of our own data. So we'll import from Torch Vision, import transforms, and we're going to create a train transform, which is equal to transforms.compose. We'll pass it in there. And this is going to be very similar to what we've done before in terms of composing a transform. What do we want to do? Well, let's say we wanted to resize one of our images or an image going through this transform. Let's change its size to 224, which is a common size in image classification. And then it's going to go through transforms. We're going to pass in trivial augment wide. And there's a parameter here, which is number of magnitude bins, which is basically a number from 0 to 31, 31 being the max, of how intense you want the augmentation to happen. So say we only put this as 5, our augmentation would be of intensity from 0 to 5. And so in that case, the maximum wouldn't be too intense. So if we put it to 31, it's going to be the max intensity. And what I mean by intensity is, say this rotation, if we go on a scale of 0 to 31, this may be a 10. Whereas 31 would be completely rotating. And same with all these others, right? So the lower this number, the less the maximum upper bound of the applied transform will be. Then if we go transforms dot to tensor, wonderful. So there we've just implemented trivial augment. How beautiful is that? That is from the PyTorch Torch Vision transforms library. We've got trivial augment wide, and it was used, trivial augment, to train the latest state-of-the-art vision models in the PyTorch Torch Vision models library or models repository. And if you wanted to look up trivial augment, how could you find that? You could search it. Here is the paper if you'd like to read it, how it's implemented. It's actually a very, very, I would say, let's just say trivial augment. I didn't want to say simple because I don't want to downplay it. Trivial augment leverages the power of randomness quite beautifully. So I'll let you read more on there. I would rather try it out on our data and visualize it first. Test transform. Let's go transforms, compose. And you might have the question of, which transforms should I use with my data? Well, that's the $1,000,000 question, right? That's the same thing as asking, which model should I use for my data? There's a fair few different answers there, and my best answer will be try out a few, see what worked for other people like we've done here by finding that trivial augment worked well for the PyTorch team. Try that on your own problems. If it works well, excellent. If it doesn't work well, you can always, excuse me, we've got a spelling mistake. If it doesn't work well, you can always set up an experiment to try something else. So let's test out our augmentation pipeline. So we'll get all the image paths. We've already done this, but we're going to do it anyway again, just to reiterate. We've covered a fair bit here, so I might just rehash on a few things. We're going to get list, image path, which is our, let me just show you, our image path. We just want to get all of the images within this file. So we'll go image path.glob, glob together all the files and folders that match this pattern. And then if we check, what do we get? We'll check the first 10. Beautiful. And then we can leverage our function from before to plot some random images. Plot random images. We'll pass in, or plot transformed, random transformed images. That's what we want. Let's see what it looks like when it goes through our trivial augment. So image paths equals image path list. This is a function that we've created before, by the way. Transform equals train transform, which is the transform we just created above. That contains trivial augment. And then we're going to put n equals 3 for 5 images, and we'll do seed equals none to plot, n equals 3 for 3 images, not 5. Beautiful. And we'll set the seed equals none, by the way. So look at this. We've got class pizza. Now, trivial augment, it resized this. Now, I'm not quite sure what it did to transform it per se. Maybe it got a little bit darker. This one looks like it's been, the colors have been manipulated in some way, shape, or form. And this one looks like it's been resized, and not too much has happened to that one from my perspective. So if we go again, let's have a look at another 3 images. So trivial augment works, and what I said before, it harnesses the power of randomness. It kind of selects randomly from all of these other augmentation types and applies them at some level of intensity. So all of these ones here, trivial augment's just going to select some at random and then apply them at some random intensity from 0 to 31, because that's what we've set on our data. And of course, you can read a little bit more in the documentation, in the paper here. but I like to see it happening. So this one looks like it's been cut off over here a little bit. This one, again, the colors have been changed in some way, shape, or form. This one's been darkened. And so do you see how we're artificially adding diversity to our training data set? So instead of all of our images being this one perspective like this, we're adding a bunch of different angles and telling our model, hey, you got to try and still learn these patterns even if they've been manipulated. So we'll try one more of these. So look at that one. That's pretty manipulated there, isn't it? But it's still an image of steak. So that's what we're trying to get our model to do, is still recognize this image as an image of steak, even though it's been manipulated a bit. Now, will this work or not? Hey, it might not, but that's all the nature of experimentation is. So play around. I would encourage you to go in the transforms documentation like we've just done, illustrations. Change this one out, trivial augment wide, for another type of augmentation that you can find in here, and see what it does to some of our images randomly. I've just highlighted trivial augment because it's what the PyTorch team have used in their most recent blog post for their training recipe to train state-of-the-art vision models. So speaking of training models, let's move forward, and we've got to build our first model for this section. I'll see you in the next video. Welcome back. In the last video, we covered how the PyTorch team used trivial augment wide, which is the latest state-of-the-art in data augmentation at the time of recording this video, to train their latest state-of-the-art computer vision models that are within Torch Vision. And we saw how easily we could apply trivial augment thanks to torchvision.transforms. And we'll just see one more of those in action, just to highlight what's going on. So it doesn't look like much happened to that image when we augment it, but we see this one has been moved over. We've got some black space there. This one has been rotated a little, and now we've got some black space there. But now's time for us to build our first computer vision model on our own custom data set. So let's get started. We're going to go model 0. We're going to reuse the tiny VGG architecture, which we covered in the computer vision section. And the first experiment that we're going to do, we're going to build a baseline, which is what we do with model 0. We're going to build it without data augmentation. So rather than use trivial augment, which we've got up here, which is what the PyTorch team used to train their state-of-the-art computer vision models, we're going to start by training a computer vision model without data augmentation. And then so later on, we can try one to see with data augmentation to see if it helps or doesn't. So let me just put a link in here, CNN Explainer. This is the model architecture that we covered in depth in the last section. So we're not going to go spend too much time here. All you have to know is that we're going to have an input of 64, 64, 3 into multiple different layers, such as convolutional layers, ReLU layers, max pool layers, and then we're going to have some output layer that suits the number of classes that we have. In this case, there's 10 different classes, but in our case, we have 3 different classes, one for pizza, steak, and sushi. So let's replicate the tiny VGG architecture from the CNN Explainer website. And this is going to be good practice, right? We're not going to spend too much time referencing their architecture. We're going to spend more time coding here. But of course, before we can train a model, what do we have to do? Well, let's go 7.1. We're going to create some transforms and loading data. We're going to load data for model 0. Now, we could, of course, use some of the variables that we already have loaded, but we're going to recreate them just to practice. So let's create a simple transform. And what is our whole premise of loading data for model 0? We want to get our data from the data folder, from pizza, steak, sushi, from the training and test folders, from their respective folders. We want to load these images and turn them into tensors. Now, we've done this a few times now, and one of the ways that we can do that is by creating a transform equals transforms.compose, and we're going to pass in, let's resize it. So transforms.resize, we're going to resize our images to be the same size as the tiny VGG architecture on the CNN Explainer website, 64, 64, 3. And then we're also going to pass in another transform to tensor so that our images get resized to 64, and then they get converted into tensors. And particularly, these values within that tensor are going to be between 0 and 1. So there's our transform. Now we're going to load some data. If you want to pause the video here and try to load it yourself, I'd encourage you to try out option 1, loading image data using the image folder class, and then turn that data set, that image folder data set, into a data loader. So batchify it so that we can use it with a PyTorch model. So give that a shot. Otherwise, let's go ahead and do that together. So 1, we're going to load and transform data. We've done this before, but let's just rehash on it what we do. So from Torch Vision, import datasets. Then we're going to create the train data simple. And I call this simple because we're going to use at first a simple transform, one with no data augmentation. And then later on for another modeling experiment, we're going to create another transform, one with data augmentation. So let's put this here, datasets, image folder, and let's go the root equals the training directory. And then the transform is going to be what? It's going to be our simple transform that we've got above. And then we can put in test data simple here. And we're going to create datasets.image folder. And then we're going to pass in the root as the test directory. And we'll pass in the transform is going to be the simple transform again above. So we're performing the same transformation here on our training data and on our testing data. Then what's the next step we can do here? Well, we can turn the data sets into data loaders. So let's try it out. First, we're going to import OS. Then from torch.utils.data, we're going to import DataLoader. And then we're going to set up batch size and number of workers. So let's go batch size. We're going to use a batch size of 32 for our first model. Num workers, which will be the number of, excuse me, got a typo up here, classic. Number of workers, which will be the what? The number of CPU cores that we dedicate towards loading our data. So let's now create the data loaders. We're going to create train data loader simple, which will be equal to data loader. And the data set that goes in here will be train data simple. Then we can set the batch size equal to the batch size parameter that we just created, or hyperparameter that is. Recall a hyperparameter is something that you can set yourself. We would like to shuffle the training data, and we're going to set num workers equal to num workers. So in our case, how many cores does Google Colab have? Let's just run this, find out how many num workers there are. I think there's going to be 2 CPUs. Wonderful. And then we're going to do the same thing for the test data loader. Test data loader simple. We're going to go data loader. We'll pass in the data set here, which is going to be the test data simple. And then we're going to go batch size equals batch size. We're not going to shuffle the test data set. And then the num workers, we'll just set it to the same thing as we've got above. Beautiful. So I hope you gave that a shot, but now do you see how quickly we can get our data loaded if it's in the right format? I know we spent a lot of time going through all of these steps over multiple videos and writing lots of code, but this is how quickly we can get set up to load our data. We create a simple transform, and then we load in and transform our data at the same time. And then we turn the data sets into data loaders just like this. Now we're ready to use these data loaders with a model. So speaking of models, how about we build the tiny VGG architecture in the next video? And in fact, we've already done this in notebook number 3. So if you want to refer back to the model that we built there, right down here, which was model number 2, if you want to refer back to this section and give it a go yourself, I'd encourage you to do so. Otherwise, we'll build the tiny VGG architecture in the next video. Welcome back. In the last video, we got set up, starting to get ready to model our first custom data set. And I issued you the challenge to try and replicate the tiny VGG architecture from the CNN Explainer website, which we covered in notebook number 3. But now let's see how fast we can do that together, hey? I'm going to write down here section 7.2. And I know we've already coded this up before, but it's good practice to see what it's like to build PyTorch models from scratch. Create tiny VGG model class. So the model is going to come from here. Previously, we created our model. There would have been one big change from the model that we created in section number 3, which is that our model in section number 3 used black and white images. But now the images that we have are going to be color images. So there's going to be 3 color channels rather than 1. And there might be a little bit of a trick that we have to do to find out the shape later on in the classifier layer. But let's get started. We've got class tinyVGG. We're going to inherit from nn.module. This is going to be the model architecture, copying tinyVGG from CNN explainer. And remember that it's quite a common practice in machine learning to find a model that works for a problem similar to yours and then copy it and try it on your own problem. So I only want 2 underscores there. We're going to initialize our class. We're going to give it an input shape, which will be an int. We're going to say how many hidden units do we want, which will also be an int. And we're going to have an output shape, which will be an int as well. And it's going to return something none, of type none. Then if we go down here, we can initialize it with super dot underscore init. Beautiful. Now let's create the first conv block. So conv block 1, which recall will be this section of layers here. So conv block 1, let's do an nn.sequential to do so. Now we need conv relu max pool. So let's try this out. And then conv 2d. The in channels is going to be the input shape of our model, the input shape parameter. The out channels is going to be the number of hidden units we have, which is from, I might just put enter down here. Input shape, hidden units. We're just getting those 2 there. Let's set the kernel size to 3, which will be how big the convolving window will be over our image data. There's a stride of 1 and the padding equals 1 as well. So these are the similar parameters to what the CNN explainer website uses. And we're going to go nn relu, and then we're going to go nn conv 2d. And I want to stress that even if someone else uses like certain values for these, you don't have to copy them exactly. So just keep that in mind. You can try out various values of these. These are all hyperparameters that you can set yourself. Hidden units, out channels equals hidden units as well. Then we're going to go kernel size equals 3, stride equals 1, and we're going to put padding equals 1 as well. Then we're going to have another relu layer, and I believe I've forgotten a comma up here. Another relu layer here, and we're going to finish it off with nn.maxpool 2d, and we're going to put in the kernel size equals 2, and the stride here equals 2. Wonderful. So, by the way, for maxpool 2d, the default stride value is same as the kernel size. So let's have a go here. What can we do now? Well, we could just replicate this block as block 2. So how about we copy this down here? We've already had enough practice writing this sort of code. So we're going to go conv block 2, but we need to change the input shape here. The input shape of this block 2 is going to receive the output shape here. So we need to line those up. This is going to be hidden units. Hidden units. And I believe that's all we need to change there. Beautiful. So let's create the classifier layer. And the classifier layer, recall, is going to be this output layer here. So we need at some point to add a linear layer that's going to have a number of outputs equal to the number of classes that we're working with. And in this case, the number of classes is 10. But in our case, our custom data set, we have 3 classes: pizza, steak, sushi. So let's create a classifier layer, which will be nn sequential. And then we're going to pass in nn.flatten to turn the outputs of our convolutional blocks into a feature vector, sorry. And then we're going to have nn.linear and the in features. Do you remember my trick for calculating the shape for in features? I'm going to put hidden units here for the time being. Out features is going to be output shape. So I've put hidden units here for the time being because we don't quite yet know what the output shape of all of these operations is going to be. Of course, we could calculate them by hand by looking up the formula for input and output shapes of convolutional layers. So the input and output shapes are here, but I prefer to just do it programmatically and let the errors tell me where I'm wrong. So we can do that by doing a forward pass. And speaking of a forward pass, let's create a forward method, because every time we have to subclass nn.module, we have to override the forward method. We've done this a few times, but as you can see, I'm picking up the pace a little bit because you've got this. So let's pass in the conv block 1. We're going to go x, then we're going to print out x.shape, and then we're going to reassign x to be self.conv block 2. So we're passing it through our second block of convolutional layers. Print x.shape to check the shape here. Now this is where our model will probably error, is because the input shape here isn't going to line up in features hidden units because we've passed all of the output of what's going through conv block 1, conv block 2 to a flatten layer, because we want a feature vector to go into our nn.linear layer, our output layer, which has an out features size of output shape. And then we're going to return x. So I'm going to print x.shape here. And I just want to let you in on one little secret as well. We haven't covered this before, but we could rewrite this entire forward method, this entire stack of code, by going return self.classifier and then going from the outside in. So we could pass in conv block 2 here, conv block 2, and then self conv block 1, and then x on the inside. So that is essentially the exact same thing as what we've done here, except this is going to benefits from operator fusion. Now, this topic is beyond the scope of this course. Essentially, all you need to know is that operator fusion behind the scenes speeds up how your GPU performs computations. So all of these are going to happen in one step. Rather than here, we are reassigning x every time we make a computation through these layers. So we're spending time going from computation back to memory, computation back to memory, whereas this kind of just chunks it all together in one hit. If you'd like to read more about this, I'd encourage you to look up the blog post, how to make your GPUs go burr from first principles. And burr means fast. That's why I love this post, right? Because it's half satire, half legitimately like GPU computer science. So if you go in here, yeah, here's what we want to avoid. We want to avoid all of this transportation between memory and compute. And then if we look in here, we might have operator fusion. There we go. This is operator fusion, the most important optimization in deep learning compilers. So I will link this, Making Deep Learning Go Burr from First Principles by Horace Hare, a great blog post that I really like, right here. So if you'd like to read more on that, it's also going to be in the extracurricular section of the course, so don't worry, it'll be there. Now, we've got a model. Oh, where did we forget a comma? Right here, of course we did. And we forgot another comma up here. Did you notice these? Beautiful. Okay, so now we can create our model by going torch or an instance of the tinyVGG to see if our model holds up. Let's create model 0 equals tinyVGG. And I'm going to pass in the input shape. What is the input shape? It's going to be the number of color channels of our image. So number of color channels in our image data, which is 3 because we have color images. And then we're going to put in hidden units equals 10, which will be the same number of hidden units as the tinyVGG architecture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, we could put in 10, we could put in 100, we could put in 64, which is a good multiple of 8. So let's just leave it at 10 for now. And then the output shape is going to be what? It's going to be the length of our class names because we want one hidden unit or one output unit per class. And then we're going to send it to the target device, which is of course CUDA. And then we can check out our model 0 here. Beautiful. So that took a few seconds, as you saw there, to move to the GPU memory. So that's just something to keep in mind for when you build large neural networks and you want to speed up their computation, is to use operator fusion where you can, because as you saw, it took a few seconds for our model to just move from the CPU, which is the default, to the GPU. So we've got our architecture here, but of course we know that this potentially is wrong. And how would we find that out? Well, we could find the right hidden unit shape, or we could find that it's wrong by passing some dummy data through our model. So that's one of my favorite ways to troubleshoot a model. Let's, in the next video, pass some dummy data through our model and see if we've implemented the forward pass correctly, and also check the input and output shapes of each of our layers. I'll see you there. In the last video, we replicated the tiny VGG architecture from the CNN Explainer website, very similar to the model that we built in section 03, but this time we're using color images instead of grayscale images. And we did it quite a bit faster than what we previously did because we've already covered it, right? And you've had some experience now building PyTorch models from scratch, so we're going to pick up the pace when we build our models. But let's now go and try a dummy forward pass to check that our forward method is working correctly and that our input and output shapes are correct. So let's create a new heading. Try a forward pass on a single image. And this is one of my favorite ways to test the model. So let's first get a single image. Get a single image. We want an image batch. Maybe we get an image batch. Get a single image batch, because we've got images that are batches already. Image batch, and then we'll get a label batch, and we'll go next, iter train data loader simple. That's the data loader that we're working with for now. And then we'll check image batch dot shape and label batch dot shape. Wonderful. And now let's see what happens. Try a forward pass. Oh, I spelt single wrong up here. Try a forward pass. We could try this on a single image. Trying it on the same batch will result in similar results. So let's go model 0, and we're just going to pass it in the image batch and see what happens. Oh no. Of course we get that input type torch float tensor and weight type torch CUDA float tensor should be the same, or input should be, so we've got tensors on a different device, right? So this is on the CPU, the image batch, whereas our model is of course on the target device. So we've seen this error a number of times. Let's see if this fixes it. Oh, we get another error, and we kind of expected this type of error. We've got runtime error, mat1 and mat2 shapes cannot be multiplied. 32, so that looks like the batch size. 2560 and 10. What is 10? Well, recall that 10 is the number of hidden units that we have. So this is the size here, that's 10 there. So it's trying to multiply a matrix of this size by this size. So 10 has got something going on with it. We need to get these two numbers, the middle numbers, to satisfy the rules of matrix multiplication, because that's what happens in our linear layer. We need to get these two numbers the same. And so our hint and my trick is to look at the previous layer. So if that's our batch size, where does this value come from? Well, could it be the fact that a tensor of this size goes through the flatten layer? Recall that we have this layer up here. So we've printed out the shape here of the conv block, the output of conv block 1. Now this shape here is the output of conv block 2. So we've got this number, the output of conv block 1, and then the output of conv block 2. So that must be the input to our classifier layer. So if we go 10 times 16 times 16, what do we get? 2,560. Beautiful. So we can multiply our hidden units, 10, by 16 by 16, which is the shape here, and we get 2560. Let's see if that works. We'll go up here, times 16 times 16, and let's see what happens. We'll rerun the model, we'll rerun the image batch, and then we'll pass it. Oh, look at that! Our model works! Well, the shapes at least line up. We don't know if it works yet. We haven't started training yet. But this is the output size. We've got the output. It's on the CUDA device, of course. But we've got 32 samples with 3 numbers in each. Now, these are going to be as good as random because we haven't trained our model yet. We've only initialized it here with random weights. So we've got 32, or a batch worth, of random predictions on 32 images. So you see how the output shape here, 3, corresponds to the output shape we set up here. Output shape equals length class names, which is exactly the number of classes that we're dealing with. But I think our number is a little bit different to what's in the CNN explainer. 1616, how did they end up with 1313? You know what? I think we got one of these numbers wrong. Kernel size, stride, padding. Let's have a look. Jump into here. If we wanted to truly replicate it, is there any padding here? I actually don't think there's any padding here. So what if we go back here and see if we can change this to 0 and change this to 0. 0. I'm not sure if this will work, by the way. If it doesn't, it's not too bad, but we're just trying to line up the shapes with the CNN explainer to truly replicate it. So the output of the conv block 1 should be 30, 30, 10. What are we working with at the moment? We've got 32, 32, 10. So let's see if removing the padding from our convolutional layers lines our shape up with the CNN explainer. So I'm going to rerun our model. I've set the padding to 0 on all of our padding hyperparameters. Oh, and we get another error. We get another shape error. Of course we do, because we've now got different shapes. Wow, do you see how often that these errors come up? Trust me, I spend a lot of time troubleshooting these shape errors. So we now have to line up these shapes. So we've got 13, 13, 10. Now does that equal 1690? Let's try it out. 13, 13, 10. 1690, beautiful. And do our shapes line up with the CNN explainer? So we've got 30, 30, 10. Remember, these are in PyTorch, so color channels first, whereas this is color channels last. So yep, we've got the output of our first conv block is lining up here, that's correct. And then same with the second block. How good is that? We've officially replicated the CNN explainer model. So we can take this value, 13, 13, 10, and bring it back up here. 13, 13, 10. Remember, hidden units is 10, so we're just going to multiply it by 13, 13. You could calculate these shapes by hand, but my trick is I like to let the error codes give me a hint of where to go. And boom, there we go. We get it working again. Some shape troubleshooting on the fly. So now we've done a single forward pass on the model. We can kind of verify that our data at least flows through it. What's next? Well, I'd like to show you another little package that I like to use to also have a look at the input and output shapes of my model. And that is called torchinfo. So you might want to give this a shot before we go into the next video. But in the next video, we're going to see how we can use torchinfo to print out a summary of our model. So we're going to get something like this. So this is how beautifully easy torchinfo is to use. So give that a shot. Install it into Google Colab and run it in a cell here. See if you can get something similar to this output for our model 0. And I'll see you in the next video. We'll try that together. In the last video, we checked our model by doing a forward pass on a single batch. And we learned that our forward method so far looks like it's intact and that we don't get any shape errors as our data moves through the model. But I'd like to introduce to you one of my favorite packages for finding out information from a PyTorch model, and that is torchinfo. So let's use torchinfo to get an idea of the shapes going through our model. So you know how much I love doing things in a programmatic way? Well, that's what torchinfo does. Before, we used print statements to find out the different shapes going through our model. And I'm just going to comment these out in our forward method so that when we run this later on during training, we don't get excessive printouts of all the shapes. So let's see what torchinfo does. And in the last video, I issued a challenge to give it a go. It's quite straightforward of how to use it, but let's see it together. This is the type of output we're looking for from our tiny VGG model. And of course, you could get this type of output from almost any PyTorch model. But we have to install it first. And as far as I know, Google Colab doesn't come with torchinfo by default. Now, you might as well try this in the future and see if it works. But yeah, I don't get this module because my Google Colab instance doesn't have it installed. No problem with that. Let's install torchinfo here. Install torchinfo, and then we'll import it if it's available. So we're going to try and import torchinfo. If it's already installed, we'll import it. And then if it doesn't work, if that try block fails, we're going to run pip install torchinfo, and then we will import torchinfo. And then we're going to run down here from torchinfo, import summary. And then if this all works, we're going to get a summary of our model. We're going to pass it in model 0. And we have to put in an input size here. Now that is an example of the size of the data that will flow through our model. So in our case, let's put in an input size of 1, 3, 64, 64. So this is an example of putting in a batch of one image. You could potentially put in 32 here if you wanted, but let's just put in a batch of a singular image. And of course, we could change these values here if we wanted to. 224, 224. But what you might notice is that if it doesn't get the right input size, it produces an error. There we go. So just like we got before when we printed out our input sizes manually, we get an error here. Because what torchinfo behind the scenes is going to do is it's going to do a forward pass on whichever model you pass it with an input size of whichever input size you give it. So let's put in the input size that our model was built for. Wonderful. So what torchinfo gives us is, we didn't comment out the printouts before. So just make sure we've commented out these printouts in the forward method of our tiny VGG class. So I'm just going to run this. Then we run that, just to make sure everything still works. We'll run torchinfo. There we go. So no printouts from our model, but look how beautiful this is. I love how this prints out. So we have our tiny VGG class, and then we can see it's comprised of 3 sequential blocks. And then inside those sequential blocks, we have different combinations of layers. We have some conv layers, some relu layers, some max pool layers, and then the final layer is our classification layer with a flatten and a linear layer. And we can see the shapes changing throughout our model as our data goes in and gets manipulated by the various layers. So are these in line with the CNN explainer? So if we check this last one, we've already verified this before. And we also get some other helpful information down here, which is total params. So you can see that each of these layers has a different amount of parameters to learn. Now, recall that a parameter is a value such as a weight or a bias term within each of our layers, which starts off as a random number, and the whole goal of deep learning is to adjust those random numbers to better represent our data. So in our case, we have just over 8,000 total parameters. Now, this is actually quite small. In the future, you'll probably play around with models that have 1 million parameters or more, and models now are starting to have many billions of parameters. And we also get some information here, such as how much the model size would be. Now, this would be very helpful depending on where we had to put our model. So what you'll notice is that as a model gets larger, has more layers, it will have more parameters, more weights and bias terms that can be adjusted to learn patterns in data. But its input size and its estimated total size would definitely get bigger as well. So that's just something to keep in mind if you have size constraints in terms of storage in your future applications. So ours is under 1 megabyte, which is quite small, but you might find that some models in the future get up to 500 megabytes, maybe even over 1 gigabyte. So just keep that in mind for going forward. And that's the crux of torchinfo, one of my favorite packages. It just gives you an idea of the input and output shapes of each of your layers. So you can use torchinfo wherever you need. It should work with most of your PyTorch models. Just be sure to pass it in the right input size. You can also use it to verify, like we did before, if the input and output shapes are correct. So check that out. Big shout out to Tyler Yep and everyone who's created the torchinfo package. Now, in the next video, let's move towards training our tiny VGG model. We're going to have to create some training and test functions. If you want to jump ahead, we've already done this. So I encourage you to go back to section 6.2 in the functionizing training and test loops. And we're going to build functions very similar to this, but for our custom data set. So if you want to replicate these functions in this notebook, give that a go. Otherwise, I'll see you in the next video and we'll do it together. How'd you go? Did you give it a shot? Did you try replicating the train step and the test step function? I hope you did. Otherwise, let's do that in this video, but this time we're going to do it for our custom data sets. And what you'll find is not much, if anything, changes because we've created our train and test loop functions in such a way that they're generic. So we want to create a train step function. And by generic, I mean they can be used with almost any model and data loader. So train step takes in a model and data loader and trains the model on the data loader. And we also want to create another function called test step, which takes in a model and a data loader and other things and evaluates the model on the data loader. And of course, for the train step and for the test step, each of them respectively are going to take a training data loader. Oh, I just might make this a third heading so that our outline looks nice and beautiful. Section 7 is turning out to be quite a big section. Of course, we want them to be respectively taking their own data loader. So train takes in the train data loader, test takes in the test data loader. Without any further ado, let's create the train step function. Now we've seen this one in the computer vision section. So let's see what we can make here. So we need a train step, which is going to take in a model, which will be a torch nn.module. And we want it also to take in a data loader, which will be a torch.utils.data loader. And then it's going to take in a loss function, which is going to be a torch nn.module as well. And then it's going to take in an optimizer, which is going to be torch optim.optimizer. Wonderful. And then what do we do? What's the first thing that we do in a training step? Well, we put the model in train mode. So let's go model.train. Then what should we do next? Well, let's set up some evaluation metrics, one of them being loss and one of them being accuracy. So set up train loss and train accuracy values. And we're going to accumulate these per batch because we're working with batches. So we've got train loss and train acc equals 0, 0. Now we can loop through our data loader. So let's write loop through data loader, and we'll loop through each of the batches in this because we've batchified our data loader. So for batch xy in enumerate data loader, we want to send the data to the target device. So we could even put that device parameter up here. Device equals device. We'll set that to device by default. And then we can go x, y equals x.to device and y.to device. Beautiful. And now what do we do? Well, remember the PyTorch, the unofficial PyTorch optimization song? We do the forward pass. So ypred equals model on x. And then number 2 is we calculate the loss. So calculate the loss. Let's go loss equals loss function, and we're going to pass it in ypred y. We've done this a few times now, So that's why we're doing it a little bit faster. So I hope you notice that the things that we've covered before, I'm stepping up the pace a bit. So it might be a bit of a challenge, but that's all right. You can handle it. And then, so that's accumulating the loss. So we're starting from 0 up here, and then each batch we're doing a forward pass, calculating the loss, and then adding it to the overall train loss. And so we're going to optimize a 0 grad, so 0 the gradients of the optimizer for each new batch. And then we're going to perform back propagation. So loss backwards, and then 5, what do? Optimize a step, step, step. Wonderful, look at that. Look at us coding a train loop in a minute or so. Now let's calculate the accuracy and accumulate it. Calculate the... You notice that we don't have an accuracy function here. That's because accuracy is quite a straightforward metric to calculate. So we'll first get the ypred class, because this is going to output model logits. As we've seen before, the raw output of a model is logits. So to get the class, we're going to take the argmax torch.softmax, so we'll get the prediction probabilities of ypred, which is the raw logits, what we've got up here, across dimension 1, and then also across dimension 1 here. Beautiful. So that should give us the labels, and then we can find out if this is wrong by checking it later on. And then we're going to create the accuracy by taking the ypred class, checking for equality with the right labels. So this is going to give us how many of these values equal true, and we want to take the sum of that, take the item of that, which is just a single integer, and then we want to divide it by the length of ypred. So we're just getting the total number that are right and dividing it by the length of samples. So that's the formula for accuracy. Now we can come down here outside of the batch loop. We know that because we've got this helpful line drawn here. And we can go adjust metrics to get the average loss and accuracy per batch. So we're going to set train loss is equal to train loss divided by the length of the data loader, so the number of batches in total, and the train accuracy is the train acc divided by the length of the data loader as well. So that's going to give us the average loss and average accuracy per epoch across all batches. So train acc. Now that's a pretty good looking function to me for a train step. Do you want to take on the test step? So pause the video, give it a shot, and you'll get great inspiration from this notebook here. Otherwise, we're going to do it together in 3, 2, 1. Let's do the test step. So create a test step function. So we want to be able to call these functions in an epoch loop. And that way, instead of writing out training and test code for multiple different models, we just write it out once and we can call those functions. So let's create def test step. We're going to do model, which is going to be, if I could type, torch nn module. And then we're going to do data loader, which is torch utils.data.dataloader. Capital L there. And then we're going to just pass in a loss function here because we don't need an optimizer for the test function. We're not trying to optimize anything. We're just trying to evaluate how our model did on the training data set. And let's put in the device here, why not? That way we can change the device if we need to. So put model in eval mode because we're going to be evaluating or we're going to be testing. Then we can set up test loss and test accuracy values. So test loss and test acc. We're going to make these 0. We're going to accumulate them per batch. But before we go through the batch, let's turn on inference mode. So this is behind the scenes going to take care of a lot of PyTorch functionality that we don't need. That's very helpful during training, such as tracking gradients, but during testing, we don't need that. So loop through data loader or data batches, and we're going to go for batch x, y in enumerate data loader. You'll notice that above we didn't actually use this batch term here, and we probably won't use it here either, but I just like to go through and have that there in case we wanted to use it anyway. So send data to the target device. So we're going to go x, y equals x.toDevice, and same with y.toDevice. Beautiful. And then what do we do for an evaluation step or a test step? Well, of course, we do the forward pass, and we're going to, let's call these test pred logits, and get the raw outputs of our model, and then we can calculate the loss on those raw outputs, calculate the loss. We'll get the loss is equal to loss function on test pred logits versus y, and then we're going to accumulate the loss. So test loss plus equals loss.item. Remember, item just gets a single integer from whatever term you call it on. And then we're going to calculate the accuracy. Now we can do this exactly how we've done for the training data set or the training step. So test pred labels, we're going to, I just want to highlight the fact that you actually don't need to take the softmax here. You could just take the argmax directly from this. The reason why we take the softmax, so you could do the same here. You could just directly take the argmax of the logits. The reason why we get the softmax is just for completeness. So if you wanted the prediction probabilities, you could use torch.softmax on the prediction logits, but it's not 100% necessary to get the same values. And you can test this out yourself. So try this with and without the softmax and see if you get the same results. So we're going to go test accuracy plus equals, now we'll just create our accuracy calculation on the fly. Test pred labels, we'll check for equality on the y, and then we'll get the sum of that, we'll get the item of that, and then we'll divide that by the length of the test pred labels. Beautiful. So it's going to give us accuracy per batch. And so now we want to adjust the metrics to get average, loss, and accuracy per batch. So test loss equals test loss divided by length of the data loader, and then we're going to go test acc equals test acc divided by length of the data loader, and then finally we're going to return the test loss, not lost, and test accuracy. Woohoo! Look at us go. Now, in previous videos, that took us, or in previous sections, that took us a fairly long time, but now we've done it in about 10 minutes or so. So give yourself a pat on the back for all the progress you've been making. But now let's, in the next video, we did this in the computer vision section as well. Did we create a train function? Oh no, we didn't, but we could. So let's create a function to functionize this. We want to train our model. I think we did actually. Def train. We've done so much. I'm not sure what we've done. Oh, okay. So looks like we might not have. But in the next video, give yourself this challenge. Create a function called train that combines these two functions and loops through them both with an epoch range. So just like we've done here in the previous notebook, can you functionize this? So just this step here. So you'll need to take in a number of epochs, you'll need to take in a train data loader and a test data loader, a model, a loss function, an optimizer, and maybe a device. And I think you should be pretty on your way to all the steps we need for train. So give that a shot, but in the next video, we're going to create a function that combines train step and test step to train a model. I'll see you there. How'd you go? In the last video, I issued you the challenge to combine our train step function as well as our test step function together in their own function so that we could just call one function that calls both of these and train a model and evaluate it, of course. So let's now do that together. I hope you gave it a shot. That's what it's all about. So we're going to create a train function. Now, the role of this function is going to, as I said, combine train step and test step. Now, we're doing all of this on purpose, right? Because we want to not have to rewrite all of our code all the time. So we want to be functionizing as many things as possible. so that we can just import these later on if we wanted to train more models and just leverage the code that we've written before as long as it works. So let's see if it does. We're going to create a train function. I'm going to first import tqdm.auto, because I'd like to get a progress bar while our model is training. There's nothing quite like watching a neural network train. So step number one is we need to create a train function that takes in various model parameters, plus optimizer, plus DataLoaders, plus a loss function, a whole bunch of different things. So let's create def train, and I'm going to pass in a model here, which is going to be torch and then .module. You'll notice that the inputs of this are going to be quite similar to our train step and test step. I don't actually need that there. So we also want a train data loader for the training data, torch.utils.data.dataloader. And we also want a test data loader, which is going to be torch.utils.data.dataloader. And then we want an optimizer. So the optimizer will only be used with our training data set, but that's okay. We can take it as an input. Optimizer. And then we want a loss function. This will generally be used for both our training and testing step, because that's what we're combining here. Now, since we're working with multi-class classification, I'm going to set our loss function to be a default of nn.crossEntropy loss. Then I'm going to get epochs. I'm going to set 5. We'll train for 5 epochs by default. And then finally, I'm going to set the device equal to the device. So, what do we get wrong here? That's all right, we'll just keep coding. We'll ignore these little red lines. If they stay around, we'll come back to them. So, step number 2. I'm going to create, this is a step you might not have seen, but I'm going to create an empty results dictionary. Now, this is going to help us track our results. Do you recall in a previous notebook, we outputted a model dictionary for how a model went? So, if we look at model 1 results, yeah, we got a dictionary like this. So I'd like to create one of these on the fly, but keep track of the result every epoch. So what was the loss on epoch number 0? What was the accuracy on epoch number 3? So we'll show you how I'll do that. We can use a dictionary and just update that while our model trains. So results, I want to keep track of the train loss. So I'm going to set that equal to an empty list and just append to it. I also want to keep track of the train accuracy. We'll set that as an empty list as well. I also want to keep track of the test loss, and I also want to keep track of the test accuracy. Now, you'll notice over time that what you can track is actually very flexible, and what your functions can do is also very flexible. So this is not the gold standard of doing anything by any means. It's just one way that works. And you'll probably find in the future that you need different functionality, and of course, you can code that out. So let's now loop through our epochs. So for epoch in TQDM, let's create a range of our epochs above. And then we can set the train loss. Have I missed a comma up here somewhere? Type annotation not supported for that type of expression. Okay, that's all right. We'll just leave that there. So we're going to go train loss and train acc. Recall that our train step function that we created in the previous video, train step returns our train loss and train acc. So as I said, I want to keep track of these throughout our training. So I'm going to get them from train step. Then for each epoch in our range of epochs, we're going to pass in our model and perform a training step. So the data loader here is of course going to be the train data loader. The loss function is just going to be the loss function that we pass into the train function. And then the optimizer is going to be the optimizer. And then the device is going to be device. Beautiful, look at that. We just performed a training step in 5 lines of code. So let's keep pushing forward. It's telling us we've got a whole bunch of different things here. Epochs is not defined. Maybe we just have to get rid of this. We can't have the type annotation here. And that'll stop Google Colab getting angry at us. If it does any more, I'm just going to ignore it for now. Epochs. Anyway, we'll leave it at that. We'll find out if there's an error later on. test loss, you might be able to find it before I do. So test step, we're going to pass in the model. We're going to pass in a data loader. Now this is going to be the test data loader. Woohoo, look at us go. Creating training and test step functions, loss function, and then we don't need an optimizer. We're just going to pass in the device, and then behind the scenes, both of these functions are going to train and test our model. How cool is that? So still within the loop, right? This is important. Within the loop, we're going to have number 4 is we're going to print out. Let's print out what's happening. Print out what's happening. We can go print, and we'll do a fancy little print statement here. We'll get the epoch, and then we will get the train loss, which will be equal to the train loss. We'll get that to, let's go 4 decimal places. How about that? And then we'll get the train accuracy, which is going to be the train ac. We'll get that to 4, maybe 3 decimal 4, just so it looks nice, looks aesthetic. And then we'll go test loss. We'll get that coming out here, and we'll pass in the test loss. We'll get that to 4 decimal places as well. And then finally, we'll get the test accuracy. So a fairly long print statement here, but that's all right. We'd like to see how our model's doing while it's training. Beautiful. And so again, still within the epoch, we want to update our results dictionary so that we can keep track of how our model performed over time. So let's pass in results. We want to update the train loss. And so this is going to be this. And then we can append our train loss value. So this is just going to expend the list in here with the train loss value every epoch. And then we'll do the same thing on the train accuracy. Append train ac. And then we'll do the same thing again with test loss. Dot append test loss. And then we will finally do the same thing with the test accuracy. Test accuracy. Now this is a pretty big function, but this is why we write the code now, so that we can use it multiple times later on. So return the filled results at the end of the epoch. So outside the epoch's loop. So our loop, we're outside it now. Let's return results. Now, I've probably got an error somewhere here, and you might be able to spot it. Okay, train data loader. Where do we get that invalid syntax? Maybe up here? Oh, we don't have a comma here. Was that the issue the whole time? Wonderful. You might have seen that. I completely missed that. But we now have a train function to train our model. And the train function, of course, is going to call out our train step function and our test step function. So what's left to do? Well, nothing less than train and evaluate model 0. So our model is way back up here. How about in the next video, we leverage our functions, namely just the train function, because it's going to call our train step function and our test step function and train our model. So I'm going to encourage you to give that a go. You're going to have to go back to the workflow maybe, or maybe you already know this. So what have we done? We've got our data ready and we turned it into tensors using a combination of these functions. We've built and picked a model. Well, we've built a model, which is the tiny VGG architecture. Have we created a loss function yet? I don't think we have. Or an optimizer? I don't think we've done that yet. We've definitely built a training loop though. We aren't using torch metrics, we're just using accuracy, but we could use this if we want. We haven't improved through experimentation yet, but we're going to try this later on. And then save and reload the model. We've seen this before. So I think we're up to picking a loss function and an optimizer. So give that a shot. In the next video, we're going to create a loss function and an optimizer, and then leverage the functions we've spent the last 2 videos creating to train our first model, model 0, on our own custom data set. This is super exciting. I'll see you in the next video. Who's ready to train and evaluate model 0? Put your hand up. I definitely am, so let's do it together. We're going to start off section 7.7, and we're going to put in train and evaluate model 0, our baseline model on our custom data set. Now, if we refer back to the PyTorch workflow,
I issued you the challenge in the last video to try and create a loss function and an optimizer. I hope you gave that a go, but we've already built a training loop. So we're going to leverage our training loop functions, namely train, train step, and test step. All we need to do now is instantiate a model, choose a loss function and an optimizer, and pass those values to our training function. So let's do that. All right, this is so exciting. Let's set the random seeds. I'm going to set torch manual seed 42 and torch CUDA manual seed 42. Now remember, I just want to highlight something. I read an article the other day about not using random seeds. The reason why we are using random seeds is for educational purposes. So to try and get our numbers on my screen and your screen as close as possible. But in practice, you quite often don't use random seeds all the time. The reason why is because you want your model's performance to be similar regardless of the random seed that you use. So just keep that in mind going forward. We're using random seeds to just exemplify how we can get similar numbers on our page, but ideally, no matter what the random seed was, our models would go in the same direction. That's where we want our models to eventually go. But we're going to train for 5 epochs, and now let's recreate an instance of tinyVGG. We can do so because we've created the tinyVGG class. So tinyVGG, which is our model 0. We don't have to do this, but we're going to do it anyway, just so we've got all the code in one place. tinyVGG, what is our input shape going to be? That is the number of color channels of our target images. And because we're dealing with color images, we have an input shape of 3. Previously, we used an input shape of 1 to deal with grayscale images. I'm going to set hidden units to 10 in line with the CNN Explainer website. And the output shape is going to be the number of classes in our training data set. And then, of course, we're going to send the target model to the target device. So what do we do now? Well, we set up a loss function and an optimizer. Loss function and optimizer. So our loss function is going to be, because we're dealing with multi-class classification, NN cross entropy, if I could spell, cross entropy loss. And then we're going to have an optimizer. This time, how about we mix things up? How about we try the Atom optimizer? Now, of course, the optimizer is one of the hyperparameters that you can set for your model, and a hyperparameter being a value that you can set yourself. So the parameters that we want to optimize are our model 0 parameters, and we're going to set a learning rate of 0.001. Now, recall that you can tweak this learning rate if you like, but I believe, did I just see that the default learning rate of Atom is 0.001? Yeah, there we go. So Atom's default learning rate is 1 to the power of 10 to the negative 3. And so that is the default learning rate for Atom. And as I said, oftentimes different variables in the PyTorch library, such as optimizers, have good default values that work across a wide range of problems. So we're just going to stick with the default. If you want to, you can experiment with different values of this. But now let's start the timer, because we want to time our models. We're going to import from timeIt. We want to get the default timer class, and I'm going to import that as timer, just so we don't have to type out default timer. So the start time is going to be timer. This is going to just put a line in the sand of what the start time is at this particular line of code. It's going to measure that, and then we're going to train model 0. Now, this is using, of course, our train function. So let's write model 0 results. I only wrote model 1, but we're not up to there yet. So let's go train model equals model 0. And this is just the training function that we wrote in a previous video. And the train data is going to be our train data loader. And we've got train data loader simple because we're not using data augmentation for model 1. And then our test data loader is going to be our test data loader simple. And then we're going to set our optimizer, which is equal to the optimizer we just created, the friendly Atom optimizer, and the loss function is going to be the loss function that we just created, which is NN cross entropy loss. Finally, we can send in epochs is going to be num epochs, which is what we set at the start of this video to 5. And of course, we could train our model for longer if we wanted to, but the whole idea of when you first start training a model is to keep your experiments quick. So that's why we're only training for 5. Maybe later on you train for 10, 20, tweak the learning rate, do a whole bunch of different things. But let's go down here. Let's end the timer, see how long our model took to train. End the timer and print out how long it took. So in a previous section, we created a helper function for this. We're just going to simplify it in this section, and we're just going to print out how long the training time was. Total training time. Let's go end time minus start time, and then we're going to go point. We'll take it to 3 decimal places, hey? Seconds. You're ready to train our first model, our first convolutional neural network on our own custom data set? On pizza, steak, and sushi images? Let's do it. You ready? 3, 2, 1. No errors. Oh, there we go. Okay. Should this be trained data loader? Did you notice that? What does our train data take as input? Oh, we're not getting a doc string. Oh, there we go. We want train data loader. Data loader, and same with this, I believe. Let's try again. Beautiful. Oh, look at that lovely progress bar. Okay, how's our model is training quite fast. Okay. All right. What do we get? So we get an accuracy on the training data set of about 40%, and we get an accuracy on the test data set of about 50%. Now, what's that telling us? It's telling us that about 50% of the time our model is getting the prediction correct, but we've only got 3 classes. So even if our model was guessing, it would get things right 33% of the time. So even if you just guessed pizza every single time, because we only have 3 classes, if you guessed pizza every single time, you get a baseline accuracy of 33%. So our model isn't doing too much better than our baseline accuracy. Of course, we'd like this number to go higher, and maybe it would if it trained for longer. So I'll let you experiment with that. But if you'd like to see some different methods of improving a model, recall back in section number 02, we had an improving a model section, improving a model. Here we go. So here's some things you might want to try. We can improve a model by adding more layers. So if we come back to our tiny VGG architecture, right up here, we're only using 2 convolutional blocks. Perhaps you wanted to add in a convolutional block 3. You can also add more hidden units. Right now we're using 10 hidden units. You might want to double that and see what happens. Fitting for longer, this is what we just spoke about. So right now we're only fitting for 5 epochs. So if you maybe wanted to try double that again, and then even double that again. Changing the activation functions. So maybe ReLU is not the ideal activation function for our specific use case. Change the learning rate. We've spoken about that before. So right now our learning rate is 0.001 for Adam, which is the default, but perhaps there's a better learning rate out there. Change the loss function. This is probably not, in our case, not going to help too much because cross-entropy loss is a pretty good loss for multi-class classification. But these are some things that you could try, these first 3 especially, you could try quite quickly. You could try doubling the layers, you could try adding more hidden units, and you could try fitting for longer. So I'd give that a shot, but in the next video, we're going to take our Model 0 results, which is a dictionary, or at least it should be, and we're going to plot some loss curves. So this is a good way to inspect how our model is training. Yeah, so we've got some values here. Let's plot these in the next video. I'll see you there. In the last video, we trained our first convolutional neural network on custom data. So you should be very proud of that. That is no small feat to take our own data set of whatever we want and train a PyTorch model on it. However, we did find that it didn't perform as well as we'd like it to. We also highlighted a few different things that we could try to do to improve it. But now let's plot our model's results using a loss curve. So I'm going to write another heading down here. We'll go, I believe we're up to 7.8. So plot the loss curves of model 0. So what is a loss curve? So I'm going to write down here. A loss curve is a way of tracking your model's progress over time. So if we just looked up Google and we looked up loss curves, oh, there's a great guide, by the way. I'm going to link this, but I'd rather, if in doubt, code it out than just look at guides. Yeah, loss curves. So yeah, loss over time. So there's our loss value on the left, and there's, say, steps, which is epochs or batches or something like that. Then we've got a whole bunch of different loss curves over here. Essentially, what we want it to do is go down over time. So that's the ideal loss curve. Well, let's go back down here. And a good guide for different loss curves can be seen here. We're not going to go through that just yet. Let's focus on plotting our own model's loss curves, and we can inspect those. Let's get the model keys. Get the model 0 results keys. I'm going to type in model 0 results.keys because it's a dictionary. Let's see if we can write some code to plot these values here. So yeah, over time. So we have one value for train loss, train ACK, test loss, and test ACK for every epoch. And of course, these lists would be longer if we train for more epochs, but let's just, how about we create a function called def plot loss curves, which will take in a results dictionary, which is of string and a list of floats. So this just means that our results parameter here is taking in a dictionary that has a string as a key, and it contains a list of floats. That's what this means here. So let's write a docstring, plots training curves of a results dictionary. Beautiful. And so we're in this section of our workflow, which is kind of like we're kind of doing something similar to TensorBoard, what it does. I'll let you look into that if you want to, otherwise we're going to see it later on. But we're really evaluating our model here. So let's write some plotting code. We're going to use matplotlib. So we want to get the loss values of the results dictionary. So this is training and test. Let's set loss equal to results train loss. So this is going to be the loss on the training data set. And then we'll create the test loss, which is going to be, we'll index on the results dictionary and get the test loss. Beautiful. Now we'll do the same and we'll get the accuracy. Get the accuracy values of the results dictionary. So training and test. And then we're going to go accuracy equals results. This will be the training accuracy, train ACK, and accuracy, or we'll call this test accuracy actually. Test accuracy equals results test ACK. Now let's create a number of epochs. So we want to figure out how many epochs we did. We can do that by just counting the length of this value here. So figure out how many epochs there were. So we'll set epochs equal to a range because we want to plot it over time, our model's results over time. That's the whole idea of a loss curve. So we'll just get the length of our results here, and we'll get the range. So now we can set up a plot. Let's go plt.figure, and we'll set the fig size equal to something nice and big because we're going to do 4 plots. We want one for, or maybe 2 plots, one for the loss, one for the accuracy. And then we will go plot the loss. plt.subplot. We're going to create 1 row, 2 columns, and index number 1. We want to put plt.plot. And here's where we're going to plot the training loss. So we'll give that a label of train loss. And then we'll add another plot with epochs and test loss. The label here is going to be test loss. And then we'll add a title, which will be loss, plt. Let's put a label on the X, which will be epochs, so we know how many steps we've done. This plot over here, loss curves, it uses steps. I'm going to use epochs. They mean almost the same thing. It depends on what scale you'd like to see your loss curves. We'll get a legend as well so that the labels appear. Now we're going to plot the accuracy. So plt.subplot. Let's go 1, 2, and then index number 2 that this plot's going to be on. plt.plot. I'm going to go epochs, accuracy, and the label here is going to be train accuracy. And then we'll get on the next plot, which is actually going to be on the same plot, we'll put the test accuracy. That way we have the test accuracy and the training accuracy side by side. Test accuracy, same with the train loss and test loss. And then we'll give our plot a title. This plot's going to be accuracy. And then we're going to give it an X label, which is going to be epochs as well. And then finally we'll get the plot, the legend, a lot of plotting code here. But let's see what this looks like, eh? If we've done it all right, we should be able to pass it in a dictionary just like this and see some nice plots like this. Let's give it a go. And I'm going to call plot loss curves, and I'm going to pass in model 0 results. Alrighty then, okay, so that's not too bad. Now, why do I say that? Well, because we're looking here for mainly trends. We haven't trained our model for too long. Quantitatively, we know that our model hasn't performed at the way we'd like it to do. So we would like the accuracy on both the train and test data sets to be higher. And then of course, if the accuracy is going higher, then the loss is going to come down. So the ideal trend for a loss curve is to go down from the top left to the bottom right. In other words, the loss is going down over time. So the trend is all right here. So potentially if we train for more epochs, which I'd encourage you to give it a go, our model's loss might get lower. And the accuracy is also trending in the right way. Our accuracy, we want it to go up over time. So if we train for more epochs, these curves may continue to go on. Now, they may not. You never really know, right? You can guess these things, but until you try it, you don't really know. So in the next video, we're going to have a look at some different forms of loss curves. But before we do that, I'd encourage you to go through this guide here, Interpreting Loss Curves. So I feel like if you just search up loss curves, you're going to find Google's guide, or you could just search Interpreting Loss Curves. Because as you'll see, there's many different ways that loss curves can be interpreted. But the ideal trend is for the loss to go down over time and metrics like accuracy to go up over time. So in the next video, let's cover a few different forms of loss curves, such as the ideal loss curve, what it looks like when your model's underfitting, and what it looks like when your model's overfitting. And if you'd like to have a primer on those things, I'd read through this guide here. Don't worry too much if you're not sure what's happening. We're going to cover a bit more about loss curves in the next video. I'll see you there. In the last video, we looked at our model's loss curves and also the accuracy curves. And a loss curve is a way to evaluate a model's performance over time, such as how long it was training for. And as you'll see, if you Google some images of loss curves, you'll see many different types of loss curves. They come in all different shapes and sizes. And there's many different ways to interpret loss curves. So this is Google's testing and debugging and machine learning guide. So I'm going to set this as extra curriculum for this section. So we're up to number 8. Let's have a look at what should an ideal loss curve look like. So we'll just link that in there. Now, loss curve, I'll just rewrite here, is a loss curve is, I'll just make some space. A loss curve is one of the most helpful ways to troubleshoot a model. So the trend of a loss curve, you want it to go down over time, and the trend typically of an evaluation metric like accuracy, you want it to go up over time.
So let's go into the keynote, loss curves. So a way to evaluate your model's performance over time. These are three of the main different forms of loss curve that you'll face, but again, there's many different types as mentioned in here, interpreting loss curves. Sometimes you get it going all over the place. Sometimes your loss will explode. Sometimes your metrics will be contradictory. Sometimes your testing loss will be higher than your training loss. We'll have a look at what that is. Sometimes your model gets stuck. In other words, the loss doesn't reduce. Let's have a look at some loss curves here in the case of underfitting, overfitting, and just right. So this is the Goldilocks zone. Underfitting is when your model's loss on the training and test data sets could be lower. So in our case, if we go back to our loss curves, of course we want this to be lower and we want our accuracy to be higher. So from our perspective, it looks like our model is underfitting. And we would probably want to train it for longer, say 10, 20 epochs to see if this trend continues. If it keeps going down, it may stop underfitting. So underfitting is when your loss could be lower. Now, the inverse of underfitting is called overfitting. And so two of the biggest problems in machine learning is trying to reduce underfitting, so in other words, make your loss lower, and also reduce overfitting. These are both active areas of research because you always want your model to perform better, but you also want it to perform pretty much the same on the training set as it does the test set. And so overfitting would be when your training loss is lower than your testing loss. And why would this be overfitting? So it means overfitting because your model is essentially learning the training data too well. And that means the loss goes down on the training data set, which is typically a good thing. However, this learning is not reflected in the testing data set. So your model is essentially memorizing patterns in the training data set that don't generalize well to the test data set. So this is where we come to the just right curve, is that we want ideally our training loss to reduce as much as our test loss. And quite often you'll find that the loss is slightly lower on the training set than it is on the test set. And that's just because the model is exposed to the training data and it's never seen the test data before. So it might be a little bit lower on the training data set than on the test data set. So underfitting, the model's loss could be lower. Overfitting, the model is learning the training data too well. Now this would be equivalent to say you were studying for a final exam and you just memorized the course materials, the training set, and when it came time to the final exam, because you'd only memorized the course materials, you couldn't adapt those skills to questions you hadn't seen before. So the final exam would be the test set. So that's overfitting. The train loss is lower than the test loss. And just right, ideally, you probably won't see loss curves this exact smooth. I mean, they might be a little bit jumpy. Ideally, your training loss and test loss go down at a similar rate. And of course, there's more combinations of these. If you'd like to see them, check out the Google's loss curve guide that you can check that up there. That's some extra curriculum. Now, you probably want to know, how do you deal with underfitting and overfitting? Let's look at a few ways. We'll start with overfitting. So we want to reduce overfitting. In other words, we want our model to perform just as well on the training data set as it does on the test data set. So one of the best ways to reduce overfitting is to get more data. So this means that our training data set will be larger, our model will be exposed to more examples, and will thus, in theory, it doesn't always work. These all come with a caveat, right? They don't always work, as with many things in machine learning. So get more data. Give your model more chance to learn patterns, generalizable patterns in a data set. You can use data augmentation, so make your model's training data set harder to learn. So we've seen a few examples of data augmentation. You can get better data, so not only more data, perhaps the data that you're using isn't that, the quality isn't that good. So if you enhance the quality of your data set, your model may be able to learn better, more generalizable patterns and in turn reduce overfitting. Use transfer learning. So we're going to cover this in a later section of the course, but transfer learning is taking one model's that works, taking its patterns that it's learned and applying it to your own data set. So for example, I'll just go into the Torch Vision models library. Many of these models in here, in Torch Vision, the models module, have already been trained on a certain data set, and such as ImageNet, and you can take the weights or the patterns that these models have learned, and if they work well on an ImageNet data set, which is millions of different images, you can adjust those patterns to your own problem. And oftentimes that will help with overfitting. If you're still overfitting, you can try to simplify your model. Usually this means taking away things like extra layers, taking away more hidden units. So say you had 10 layers, you might reduce it to 5 layers. Why does this, what's the theory behind this? Well, if you simplify your model and take away complexity from your model, you're kind of telling your model, hey, use what you've got, and you're going to have to, because you've only got 5 layers now, you're going to have to make sure that those 5 layers work really well because you've no longer got 10. And the same for hidden units. Say you started with 100 hidden units per layer, you might reduce that to 50 and say, hey, you had 100 before, now use those 50 and make your patterns generalizable. Use learning rate decay. So the learning rate is how much your optimizer updates your model's weights every step. So learning rate decay is to decay the learning rate over time. So you might look this up. You can look this up, go PyTorch learning rate scheduling. So what this means is you want to decrease your learning rate over time. Now I know I'm giving you a lot of different things here, but you've got this keynote as a reference, so you can come across these over time. So learning rate scheduling. So we might look into here. Do we have schedule? Scheduler. Beautiful. So this is going to adjust the learning rate over time. So for example, at the start of when a model is training, you might want a higher learning rate. And then as the model starts to learn patterns more and more and more, you might want to reduce that learning rate over time so that your model doesn't update its patterns too much in later epochs. So that's the concept of learning rate scheduling. The closer you get to convergence, the lower you might want to set your learning rate. Think of it like this. If you're reaching for a coin at the back of a couch, can we get an image of that? Coin at back of couch. Images. So if you're trying to reach a coin in the cushions here, so the closer you get to that coin, at the beginning you might take big steps, but then the closer you get to that coin, the smaller the step you might take to pick that coin out. Because if you take a big step when you're really close to the coin here, the coin might fall down the couch. The same thing with learning rate decay. At the start of your model training, you might take bigger steps as your model works its way down the loss curve. But then you get closer and closer to the ideal position on the loss curve. You might start to lower and lower that learning rate until you get right very close to the end and you can pick up the coin. Or in other words, your model can converge. And then finally, use early stopping. So if we go into an image, is there early stopping here? Early stopping. Loss curves, early stopping. So what this means is that you stop. Yeah, there we go. So there's heaps of different guides. Early stopping with PyTorch, beautiful. So what this means is before your testing error starts to go up, you keep track of your model's testing error, and then you stop your model from training, or you save the weights, or you save the patterns where your model's loss was the lowest. So then you could just set your model to train for an infinite amount of training steps. And as soon as the testing error starts to increase for, say, 10 steps in a row, you go back to this point here and you go, I think that was where our model was the best, and the testing error started to increase after that, so we're going to save that model there instead of the model here. So that's the concept of early stopping. So that's dealing with overfitting. There are other methods to deal with underfitting. So recall, underfitting is when we have a loss that isn't as low as we'd like it to be. Our model is not fitting the data very well, so it's underfitting. So to reduce underfitting, you can add more layers/units to your model. You're trying to increase your model's ability to learn by adding more layers or units. You can again tweak the learning rate. Perhaps your learning rate is too high to begin with and your model doesn't learn very well. So you can adjust the learning rate again, just like we discussed with reaching for that coin at the back of a couch. If your model is still underfitting, you can train for longer. So that means giving your model more opportunities to look at the data. So more epochs, that just means it's got looking at the training set over and over and over and over again and trying to learn those patterns. However, you might find again, if you try to train for too long, your testing error will start to go up. Your model might start overfitting if you train too long. So machine learning is all about a balance between underfitting and overfitting. You want your model to fit quite well. And so this is a great one. So you want your model to start fitting quite well, but then if you try to reduce underfitting too much, you might start to overfit, and then vice versa, right? If you try to reduce overfitting too much, your model might underfit. So this is one of the most fun dances in machine learning, the balance between overfitting and underfitting. Finally, you might use transfer learning. So transfer learning helps with overfitting and underfitting. Recall transfer learning is using a model's learned patterns from one problem and adjusting them to your own. We're going to see this later on in the course. And then finally, use less regularization. So regularization is holding your model back. So it's trying to prevent overfitting. So if you do too much preventing of overfitting, in other words, regularizing your model, you might end up underfitting. So if we go back, we have a look at the ideal curves. Underfitting, if you try to prevent underfitting too much, so increasing your model's capability to learn, you might end up overfitting. And if you try to prevent overfitting too much, you might end up underfitting. We are going for the just right section. And this is going to be a balance between these two throughout your entire machine learning career. In fact, it's probably the most prevalent area of research is trying to get models not to underfit, but also not to overfit. So keep that in mind. A loss curve is a great way to evaluate your model's performance over time. And a lot of what we do with the loss curves is try to work out whether our model is underfitting or overfitting, and we're trying to get to this just right curve. We might not get exactly there, but we want to keep trying getting as close as we can. So with that being said, let's now build another model in the next video, and we're going to try a method to try and see if we can use data augmentation to prevent our model from overfitting. Although that experiment doesn't sound like the most ideal one we could do right now, because it looks like our model is underfitting. So with your knowledge of what you've just learned in the previous video, how to prevent underfitting, what would you do to increase this model's capability of learning patterns in the training data set? Would you train it for longer? Would you add more layers? Would you add more hidden units? Have a think, and we'll start building another model in the next video. Welcome back. In the last video, we covered the important concept of a loss curve and how it can give us information about whether our model is underfitting. In other words, our model's loss could be lower, or whether it's overfitting. In other words, the training loss is lower than the test loss, or far lower than the validation loss. That's another thing to note here, is that I've put training and test sets here. You could also do this with a validation data set. And that the just right, the Goldilocks zone, is when our training and test loss are quite similar over time. Now, there was a fair bit of information in that last video, so just wanted to highlight that you can get this all in section 04, which is the notebook that we're working on. And then if you come down over here, if we come to section 8, what should an ideal loss curve look like? We've got underfitting, overfitting, just right, how to deal with overfitting. We've got a few options here. We've got how to deal with underfitting, and then we've got a few options there. And then if we wanted to look for more, how to deal with overfitting. You could find a bunch of resources here, and then how to deal with underfitting. You could find a bunch of resources here as well. So that is a very fine line, very fine balance that you're going to experience throughout all of your machine learning career. But it's time now to move on. We're going to move on to creating another model, which is TinyVGG with data augmentation this time. So if we go back to the slide, data augmentation is one way of dealing with overfitting. Now, it's probably not the most ideal experiment that we could take because our model 0, our baseline model, looks like it's underfitting. But data augmentation, as we've seen before, is a way of manipulating images to artificially increase the diversity of your training data set without collecting more data. So we could take our photos of pizza, sushi, and steak and randomly rotate them 30 degrees. And increased diversity forces a model to learn, or hopefully learn. Again, all of these come with a caveat of not always being the silver bullet, to learn more generalizable patterns. Now, I should have spelled generalizable here rather than generalization, but similar thing. Let's go here. Let's create, to start off with, we'll just write down. Now let's try another modeling experiment. So this is in line with our PyTorch workflow, trying a model, then trying another one, and trying another one, so and so over again. This time using the same model as before, but with some slight data augmentation. Oh, maybe not slight, that's probably not the best word. We'll just say with some data augmentation. And if we come down here, we're going to write section 9.1. We need to first create a transform with data augmentation. So we've seen what this looks like before. We're going to use the trivial augment data augmentation, create training transform, which is, as we saw in a previous video, what the PyTorch team have recently used to train their state-of-the-art computer vision models. So train transform trivial. This is what I'm going to call my transform. And I'm just going to, from Torch Vision, import transforms. We've done this before. We don't have to re-import it, but I'm going to do it anyway just to show you that we're re-importing, or we're using transforms. And we're going to compose a transform here. Recall that transforms help us manipulate our data. So we're going to transform our images into size 64 by 64. Then we're going to set up a trivial augment transforms, just like we did before. Trivial augment wide. And we're going to set the number of magnitude bins here to be 31, which is the default here, which means we'll randomly use some data augmentation on each one of our images, and it will be applied at a magnitude of 0 to 31, also randomly selected. So if we lowered this to 5, the upper bound of intensity of how much that data augmentation is applied to a certain image will be less than if we set it to, say, 31. Now, our final transform here is going to be 2 tensor because we want our images in tensor format for our model. And then I'm going to create a test transform. I'm going to call this simple, which is just going to be transforms.compose. And all that it's going to have, oh, I should put a list here. All that it's going to have, I'll just make some space over here, is going to be transforms. All we want to do is resize the image. Size equals 64, 64. Now, we don't apply data augmentation to the test data set because we only just want to evaluate our models on the test data set. Our models aren't going to be learning any generalizable patterns on the test data set, which is why we focus our data augmentations on the training data set. And I've just readjusted that. I don't want to do that. Beautiful. So we've got a transform ready. Now let's load some data using those transforms. So we'll create train and test data sets and DataLoaders with data augmentation. So we've done this before. You might want to try it out on your own. So pause the video if you'd like to test it out. Create a data set and a data loader using these transforms here. And recall that our data set is going to be creating a data set from pizza, steak, and sushi for the train and test folders. And that our data loader is going to be batchifying our data set. So let's turn our image folders into data sets. Data sets, beautiful. And I'm going to write here train data augmented, just so we know that it's been augmented. We've got a few of similar variable names throughout this notebook, so I just want to be as clear as possible. And I'm going to use, I'll just re-import Torch Vision datasets. We've seen this before, the image folder. So rather than use our own custom class, we're going to use the existing image folder class that's within Torch Vision datasets. And we have to pass in here a root. So I'll just get the doc string there. root, which is going to be equal to our train dir, which recall is the path to our training directory. I've got that saved. And then I'm going to pass in here that the transform is going to be train transform trivial. So our training data is going to be augmented thanks to this transform here, and transforms trivial augment wide. You know where you can find more about trivial augment wide, of course, in the PyTorch documentation, or just searching transforms trivial augment wide. And did I spell this wrong? Trivial. Oh, train transform. I spelled that wrong. Of course I did. So test data, let's create this as test data simple equals datasets.image folder. And the root dir is going to be here, the test directory. And the transform is just going to be what? The test transform simple. Beautiful. So now let's turn these data sets into data loaders. So turn our data sets into data loaders. We're going to import OS. I'm going to set the batch size here to equal to 32. The number of workers that are going to load our data loaders, I'm going to set this to os.cpu count. So there'll be one worker per CPU on our machine. I'm going to set here the torch manual seed to 42 because we're going to shuffle our training data. Train data loader, I'm going to call this augmented, equals data loader. Now I don't need to re-import this, but I just want to show you again. From torch.utils, you can never have enough practice, right? .data, let's import data loader. So that's where we got the data loader class from. Now let's go train data augmented. We'll pass in that as the data set. And I'll just put in here the parameter name for completeness. That's our data set. And then we want to set the batch size, which is equal to batch size. I'm going to set shuffle equal to true, and I'm going to set num workers equal to num workers. Beautiful. And now let's do that again with the test data loader this time. Test data loader, I'm going to call this test data loader simple. We're not using any data augmentation on the test data set, just turning our images, our test images, into tensors. The data set here is going to be test data simple. I'm going to pass in the batch size equal to batch size, so both our data loaders will have a batch size of 32. I'm going to keep shuffle on false, and num workers I'm going to set to num workers. Look at us go. We've already got a data set and a data loader. This time our data loader is going to be augmented for the training data set, and it's going to be nice and simple for the test data set. So this is really similar, this data loader, to the previous one we made. The only difference in this modeling experiment is that we're going to be adding data augmentation, namely trivial augment wide. So with that being said, we've got a data set, we've got a data loader. In the next video, let's construct and train model 1. In fact, you might want to give that a go. So you can use our tinyVGG class to make model 1, and then you can use our train function to train a new tinyVGG instance with our training data loader augmented and our test data loader simple. So give that a go, and we'll do it together in the next video. I'll see you there. Now that we've got our data sets and data loaders with data augmentation ready, let's now create another model. So 9.3, we're going to construct and train model 1. And this time, I'm just going to write what we're going to be doing. This time we'll be using the same model architecture, but we're changing the data here. Except this time we've augmented the training data. So we'd like to see how this performs compared to a model with no data augmentation. So that was our baseline up here. And that's what you'll generally do with your experiments. You'll start as simple as possible and introduce complexity when required. So create model 1, and send it to the target device, that is, to the target device. And because of our helpful selves previously, we can create a manual seed here, torch.manual seed, and we can create model 1 leveraging the class that we created before. So although we built TinyVGG from scratch in this video, in this section, sorry, in subsequent coding sessions, because we've built it from scratch once and we know that it works, we can just recreate it by calling the class and passing in different variables here. So let's get the number of classes that we have in our train data augmented classes, and we're going to send it to device. And then if we inspect model 1, let's have a look. Wonderful. Now let's keep going. We can also leverage our training function that we did. You might have tried this before. So let's now train our model. I'm just going to put here, wonderful. Now we've got a model and DataLoaders. Let's create, what do we have to do? We have to create a loss function and an optimizer and call upon our train function that we created earlier to train and evaluate our model. Beautiful. So I'm going to set the random seeds, torch.manual seeds, and torch.CUDA, because we're going to be using CUDA. Let's set the manual seed here, 42. I'm going to set the number of epochs. We're going to keep many of the parameters the same. Set the number of epochs, num epochs equals 5. We could of course train this model for longer if we really wanted to by increasing the number of epochs. But now let's set up the loss function. So loss fn equals nn cross entropy loss. Don't forget, this just came into mind, loss function often as well in PyTorch is called criterion. So the criterion you're trying to reduce, but I just like to call it loss function. And then we're going to have optimizer. Let's use the same optimizer we used before, torch.optim.atom. Recall SGD and atom are two of the most popular optimizers. So model1.parameters, they're the parameters we're going to optimize. We're going to set the learning rate to 001, which is the default for the atom optimizer in PyTorch. Then we're going to start the timer. So from timeIt, let's import the default timer as timer. And we'll go start time equals timer. And then let's go train model 1. How can we do this? Well, we're going to get a results dictionary as model 1 results. We're going to call upon our train function. Inside our train function, we'll pass the model parameter as model 1. For the train data loader parameter, we're going to pass in train data loader augmented, so our augmented training data loader. And for the test data loader, we can pass in here test data loader simple. And then we can write our optimizer, which will be the atom optimizer. Our loss function is going to be nn cross entropy loss, what we've created above. And then we can set the number of epochs is going to be equal to num epochs. And then if we really wanted to, we could set the device equal to device, which will be our target device. And now let's end the timer and print out how long it took. End time equals timer, and we'll go print total training time for model 1 is going to be end time minus start time. And it would help if I could spell. We'll get that to 3 decimal places, and that'll be seconds. So you ready? Look how quickly we built a training pipeline for model 1. And look how easily we created it. So go us for coding all of that stuff up before. Let's train our second model. Our first model using data augmentation. You ready? 3, 2, 1, let's go. No errors. Beautiful. We're going nice and quick here. So, about just over 7 seconds. So what GPU do I have currently? Just keep this in mind that I'm using Google Colab Pro, so I get preference in terms of allocating a faster GPU. Your model training time may be longer than what I've got, depending on the GPU. It also may be faster, again, depending on the GPU. But we get about 7 seconds, but it looks like our model with data augmentation didn't perform as well as our model without data augmentation. So how long did our model before without data augmentation take to train? Oh, just over 7 seconds as well. But we got better results in terms of accuracy on the training and test data sets for model 0. So maybe data augmentation doesn't help in our case. And we kind of hinted at that because the loss here was already going down. We weren't really overfitting yet. So recall that data augmentation is a way to help with overfitting generally. So maybe that wasn't the best step to try and improve our model. But let's nonetheless keep evaluating our model. In the next video, we're going to plot the loss curves of model 1. So in fact, you might want to give that a go. So we've got a function, plot loss curves, and we've got some results in a dictionary format. So try that out, plot the loss curves, and see what you see. Let's do it together in the next video. I'll see you there. In the last video, we did the really exciting thing of training our first model with data augmentation, but we also saw that quantitatively, it looks like that it didn't give us much improvement. So let's keep evaluating our model here. I'm going to make a section. Recall that one of my favorite ways, or one of the best ways, not just my favorite, to evaluate the performance of a model over time is to plot the loss curves. So a loss curve helps you evaluate your model's performance over time. And it will also give you a great visual representation or a visual way to see if your model is underfitting or overfitting. So let's plot the loss curves of model 1 results and see what happens. We're using this function we created before. And oh my goodness, is that going in the right direction? It looks like our test loss is going up here. Now, is that where we want it to go? Remember, the ideal direction for a loss curve is to go down over time because loss is measuring what? It's measuring how wrong our model is. And the accuracy curve looks like it's all over the place as well. I mean, it's going up kind of, but maybe we don't have enough time to measure these things. So an experiment that you could do is train both of our models, model 0 and model 1, for more epochs and see if these loss curves flatten out. So I'll pose you the question, is our model underfitting or overfitting right now? Or both? So if we want to have a look at the loss curves, our just right is for the loss, that is, this is not for accuracy, this is for loss. Over time, we want it to go down. So for me, our model is underfitting because our loss could be lower, but it also looks like it's overfitting as well. So it's not doing a very good job because our test loss is far higher than our training loss. So if we go back to section 4 of the Learn PyTorch.io book, what should an ideal loss curve look like? I'd like you to start thinking of some ways that we could deal with overfitting of our model. So could we get more data? Could we simplify it? Could we use transfer learning? We're going to see that later on, but you might want to jump ahead and have a look. And if we're dealing with underfitting, what are some other things that we could try with our model? Could we add some more layers, potentially another convolutional block? Could we increase the number of hidden units per layer? So if we've got currently 10 hidden units per layer, maybe you want to increase that to 64 or something like that. Could we train it for longer? That's probably one of the easiest things to try with our current training functions. We could train for 20 epochs. So have a go at this, reference this, try out some experiments with, see if you can get these loss curves more towards the ideal shape. And in the next video, we're going to keep pushing forward. We're going to compare our model results. So we've done 2 experiments. Let's now see them side by side. We've looked at our model results individually, and we know that they could be improved. But a good way to compare all of your experiments is to compare your model's results side by side. So that's what we're going to do in the next video. I'll see you there. Now that we've compared our model's loss curves on their own individually, how about we compare our model results to each other? So let's have have a look at comparing our model results. And so I'm going to write a little note here that after evaluating our modeling experiments on their own, it's important to compare them to each other. And there's a few different ways to do this. Number one is hard coding. So like we've done, we've written functions, we've written helper functions and whatnot, and manually plotted things. So I'm just going to write in here, this is what we're doing. Then of course there are tools to do this, such as PyTorch plus TensorBoard. And so I'll link to this, PyTorch TensorBoard. We're going to see this in a later section of the course. TensorBoard is a great resource for tracking your experiments. If you'd like to jump forward and have a look at what that is in the PyTorch documentation, I'd encourage you to do so. Then another one of my favorite tools is weights and biases. So these are all going to involve some code as well, but they help out with automatically tracking different experiments. So weights and biases is one of my favorite, and you've got platform for experiments. That's what you'll be looking at. So if you run multiple experiments, you can set up weights and biases pretty easy to track your different model hyperparameters. So PyTorch, there we go. Import weights and biases, start a new run on weights and biases. You can save the learning rate value and whatnot, go through your data and just log everything there. So this is not a course about different tools. We're going to focus on just pure PyTorch, but I thought I'd leave these here anyway because you're going to come across them eventually. And ML Flow is another one of my favorites as well. We have ML tracking, projects, models, registry, all that sort of stuff. If you'd like to look into more ways to track your experiments, there are some extensions. But for now, we're going to stick with hard coding. We're just going to do it as simple as possible to begin with. And if we wanted to add other tools later on, we can sure do that. So let's create a data frame for each of our model results. We can do this because our model results, recall, are in the form of dictionaries. So model 0 results. But you can see what we're doing now by hard coding this, it's quite cumbersome. Can you imagine if we had, say, 10 models or even just 5 models? We'd have to really write a fair bit of code here for all of our dictionaries and whatnot, whereas these tools here help you to track everything automatically. So we've got a data frame here. Model 0 results over time. These are our number of epochs. We can notice that the training loss starts to go down. The testing loss also starts to go down. And the accuracy on the training and test data set starts to go up. Now, those are the trends that we're looking for. So an experiment you could try would be to train this model 0 for longer to see if it improved. But we're currently just interested in comparing results. So let's set up a plot. I want to plot model 0 results and model 1 results on the same plot. So we'll need a plot for training loss, we'll need a plot for training accuracy, test loss, and test accuracy, and then we want 2 separate lines on each of them, one for model 0 and one for model 1. And this particular pattern would be similar regardless if we had 10 different experiments or if we had 10 different metrics we wanted to compare. You generally want to plot them all against each other to make them visual. And that's what tools such as weights and biases, what TensorBoard, and what ML Flow can help you to do. So I'm just going to get out of that, clean up our browser. So let's set up a plot here. I'm going to use matplotlib, going to put in a figure. I'm going to make it quite large because we want 4 subplots, one for each of the metrics we want to compare across our different models. Now let's get number of epochs. So epochs is going to be length, or we'll turn it into a range actually. Range of len model 0 df, so that's going to give us 5. Beautiful, range between 0 and 5. Now let's create a plot for the train loss. We want to compare the train loss across model 0 and the train loss across model 1. So we can go plt.subplot. Let's create a plot with 2 rows and 2 columns, and this is going to be index number 1 will be the training loss. We'll go plt.plot. I'm going to put in here epochs and then model 0 df. Inside here, I'm going to put train loss for our first metric, and then I'm going to label it with model 0. So we're comparing the train loss on each of our modeling experiments. Recall that model 0 was our baseline model, and that was tiny VGG without data augmentation. And then we tried out model 1, which was the same model, but all we did was we added a data augmentation transform to our training data. So PLT, and we'll go X label, they both used the same test data set. And PLT.legend. Let's see what this looks like. Wonderful. So there's our training loss across two different models. So we notice that model 0 is trending in the right way. Model 1 kind of exploded on epoch number, that would be 0, 1, 2, or 1, depending how you're counting. Let's just say epoch number 2, because that's easier. The loss went up, but then it started to go back down. So again, if we continued training these models, we might notice that the overall trend of the loss is going down on the training data set, which is exactly what we'd like. So let's now plot, we'll go the test loss. So I'm going to go test loss here, and then I'm going to change this. I believe if I hold Control or Command maybe, nope, or Option on my Mac keyboard. Yeah, so it might be a different key on Windows, but for me, I can press Option, and I can get a multi-cursor here. So I'm just going to come back in here, and that way I can backspace there and just turn this into test loss. Wonderful. So I'm going to put this as test loss as the title, and I need to change the index. So this will be index 1, index 2, index 3, index 4. Let's see what this looks like. Do we get the test loss? Beautiful, that's what we get. However, we notice that model 1 is probably overfitting at this stage, so maybe the data augmentation wasn't the best change to make to our model. Recall that even if you make a change to your model, such as preventing overfitting or underfitting, it won't always guarantee that the change takes your model's evaluation metrics in the right direction. Ideally, loss is going from top left to bottom right over time. So looks like model 0 is winning out here at the moment on the loss front. So now let's plot the accuracy for both training and test. So I'm going to change this to train. I'm going to put this as accuracy. And this is going to be index number 3 on the plot. And do we save it as, yeah, just ACK. Wonderful. So I'm going to option click here on my Mac. This is going to be train, and this is going to be accuracy here. And then I'll change this one to accuracy. And then I'm going to change this to accuracy. And this is going to be plot number 4. 2 rows, 2 columns, index number 4. And I'm going to option click here to have 2 cursors, test ACK, and then I'll change this to test ACK. And I'm going to get rid of the legend here. It takes a little bit to plot because we're doing 4 graphs in one hit. Wonderful. So that's comparing our models, but do you see how we could potentially functionalize this to plot however many model results that we have? But if we had, say, another 5 models, we did another 5 experiments, which is actually not too many experiments on a problem. You might find that sometimes you do over a dozen experiments for a single modeling problem, maybe even more. These graphs can get pretty outlandish with all of the lines going through. So that's again what tools like TensorBoard, weights and biases, and MLflow will help with. But if we have a look at the accuracy, it seems that both of our models are heading in the right direction. We want to go from the bottom left up in the case of accuracy. But the test accuracy, that's training. Oh, excuse me. Is this not training accuracy? I messed up that. Did you catch that one? So training accuracy, we're heading in the right direction, but it looks like model 1 is, still overfitting. So the results we're getting on the training data set aren't coming over to the testing data set. And that's what we really want our models to shine, is on the test data set. So metrics on the training data set are good, but ideally we want our models to perform well on the test data set, data it hasn't seen before. So that's just something to keep in mind. Whenever you do a series of modeling experiments, it's always good to not only evaluate them individually, evaluate them against each other. So that way you can go back through your experiments, see what worked and what didn't. If you were to ask me what I would do for both of these models, I would probably train them for longer and maybe add some more hidden units to each of the layers and see where the results go from there. So give that a shot. In the next video, let's see how we can use our trained models to make a prediction on our own custom image of food. So yes, we used a custom data set of pizza, steak, and sushi images, but what if we had our own, what if we finished this model training and we decided, you know what, this is a good enough model, and then we deployed it to an app like Nutrify.app, which is a food recognition app that I'm personally working on. Then we wanted to upload an image and have it be classified by our PyTorch model. So let's give that a shot, see how we can use our trained model to predict on an image that's not in our training data and not in our testing data. I'll see you in the next video. Welcome back. In the last video, we compared our modeling experiments. Now we're going to move on to one of the most exciting parts of deep learning, and that is making a prediction on a custom image. So although we've trained a model on custom data, how do you make a prediction on a sample / image in our case that's not in either the training or testing data set? So let's say you are building a food recognition app such as Nutrify, take a photo of food and learn about it. You wanted to use computer vision to essentially turn foods into QR codes. So I'll just show you the workflow here. If we were to upload this image of my dad giving 2 thumbs up for a delicious pizza, and what is Nutrify predicted as? Pizza. Beautiful. So macronutrients, there you get some nutrition information and then the time taken. So we could replicate a similar process to this using our trained PyTorch model, albeit it's not going to be too great of results or performance because we've seen that we could improve our models based on the accuracy here and based on the loss and whatnot. But let's just see what it's like, the workflow. So the first thing we're going to do is get a custom image. Now we could upload one here, such as clicking the upload button in Google Colab, choosing an image, and then importing it like that. But I'm going to do so programmatically, as you've seen before. So let's write some code in this video to download a custom image. I'm going to do so using requests. And like all good cooking shows, I've prepared a custom image for us. So custom image path, but again, you could use this process that we're going to go through with any of your own images of pizza, steak, or sushi. And if you wanted to train your own model on another set of custom data, the workflow will be quite similar. So I'm going to download a photo called Pizza Dad, which is of my dad, 2 big thumbs up. And so I'm going to download it from GitHub. So this image is on the course GitHub. And let's write some code to download the image if it doesn't already exist in our Colab instance. So if you wanted to upload a single image, you could click with this button. Just beware that like all of our other data, it's going to disappear if Colab disconnects. So that's why I like to write code so we don't have to re-upload it every time. So if not custom image path.is file, let's open a request here or open a file. Going to open up the custom image path with write binary permissions as F, short for file. And then when downloading, this is because our image is stored on GitHub. When downloading an image or when downloading from GitHub in general, you typically want the raw link, need to use the raw file link. So let's write a request here equals request.get. So if we go to the PyTorch deep learning repo, then if we go into, I believe it might be extras, not in extras, it's going to be in images. That would make a lot more sense, wouldn't it, Daniel? Let's get O4 Pizza Dad. So if we have a look, this is PyTorch deep learning, images, O4 Pizza Dad. There's a big version of the image there. And then if we click download, is this going to give us the raw link? Yeah, there we go. So that's the image. Hey Dad, how you doing? Is that pizza delicious? It looks like it. Let's see if our model can get this right. What do you think? Will it? So of course we want our model to predict pizza for this image because it's got a pizza in it. So custom image path, we're going to download that. I've just put in the raw URL above. So notice the raw GitHub user content. That's from the course GitHub. Then I'm going to go f.write So file, write the request content. So the content from the request, in other words, the raw file from GitHub here. Similar workflow for if you were getting another image from somewhere else on the internet. And else, if it is already downloaded, let's just not download it. So printf custom image path already exists, skipping download. And let's see if this works. We'll run the code. So downloading data 04pizzadad.jpg. And if we go into here, we refresh. There we go. Beautiful. So our data, or our custom image, is now in our data folder. So if we click on this, this is inside Google Colab now. Beautiful. We got a nice big image there. And there's a nice big pizza there. So we're going to be writing some code over the next few videos to do the exact same process as what we've been doing to import our custom data set. For our custom image, what do we still have to do? We still have to turn it into tensors, and then we have to pass it through our model. So let's see what that looks like over the next few videos. Woohoo! We are up to one of the most exciting parts of building deep learning models, and that is predicting on custom data. In our case, a custom image of a photo of my dad eating pizza. So of course, we're training a computer vision model on here on pizza, steak, and sushi. So hopefully the ideal result for our model to predict on this image will be pizza. So let's keep going. Let's figure out how we can get our image, our custom image, our singular image into tensor form. Loading in a custom image with PyTorch, creating another section here. So I'm just going to write down here, we have to make sure our custom image is in the same format as the data our model was trained on. So namely, that was in tensor form with data type torch float32 and then of shape 64 by 64 by 3. So we might need to change the shape of our image, and then we need to make sure that it's on the right device. Command MM. Beautiful. So let's see what this looks like, hey? So if I'm going to import Torch Vision, now the package you use to load your data will depend on the domain you're in. So let's open up the Torch Vision documentation. We can go to models, that's okay. So if we're working with text, you might want to look in here for some input and output functions, so some loading functions. Torch Audio, same thing. Torch Vision is what we're working with. Let's click into Torch Vision. Now we want to look into reading and writing images and videos because we want to read in an image, right? We've got a custom image, we want to read it in. So this is part of your extracurricular, by the way, to go through these for at least 10 minutes each. So spend an hour if you're going through Torch Vision. You could do the same across these other ones. It will just really help you familiarize yourself with all the functions of PyTorch domain libraries. So we want to look, here's some options for video. We're not working with video. Here's some options for images. Now, what do we want to do? We want to read in an image. So we've got a few things here. Decode image. Oh, I've skipped over one. We can write a JPEG if we wanted to. We can encode a PNG. Let's jump into this one. Read image. What does it do? Reads a JPEG or PNG into a 3-dimensional RGB or grayscale tensor. That is what we want. And then optionally converts the image to the desired format. The values of the output tensor are uint8. Okay, beautiful. So let's see what this looks like, eh? Mode, the read mode used optionally for converting the image. Let's see what we can do with this. I'm going to copy this in. So I'll write this down. We can read an image into PyTorch using, we'll go with that. So let's see what this looks like in practice. Read in custom image. I can't explain to you how much I love using deep learning models to predict on custom data. So custom image, we're going to call it uint8 because as we read from the documentation here, it reads it in uint8 format. So let's have a look at what that looks like rather than just talking about it. torchvision.io, read image. What's our target image path? Well, we've got custom image path up here. This is why I like to do things programmatically. So if our Colab notebook reset, we could just run this cell again, get our custom image, and then we've got it here. So custom image uint8. Let's see what this looks like. Oh, what did we get wrong? Unable to cast Python instance. Oh, does it need to be a string? Expected a value type of string. Oh, but found POSIX path. So the path needs to be a string. Okay. If we have a look at our custom image path, what did we get wrong? Oh, we've got a POSIX path. So let's convert this custom image path into a string and see what happens. Look at that. That's our image in integer form. I wonder if this is plottable. Let's go plt.imshow custom image uint8. Maybe we get a dimensionality problem here. Invalid shape. Okay, let's permute it. Permute, and we'll go 1, 2, 0. Is this going to plot? It's a fairly big image. There we go, 2 thumbs up. Haha, look at us. So that is the power of torchvision.io. IO stands for input output. We were just able to read in our custom image. Now, how about we get some metadata about this? Let's go, we'll print it up here actually. I'll keep that there because that's fun to plot it. Let's find the shape of our data, the data type, and yeah, we've got it in tensor format. But it's uint8 right now. So we might have to convert that to float32. We want to find out its shape, and we need to make sure that if we're predicting on a custom image, the data that we're predicting on, the custom image, needs to be on the same device as our model. So let's print out some info. Print, let's go custom image tensor, and this is going to be a new line, and then we will go custom image uint8. Wonderful. And then let's go custom image shape. We will get the shape parameter, custom image shape, or attribute, sorry. And then we also want to know the data type, custom image data type. But we have a kind of an inkling because the documentation said it would be uint8, uint8. And we'll go dtype. Let's have a look. What do we have? So there's our image tensor. And it's quite a big image, so custom image shape. So what was our model trained on? Our model was trained on images of 64 by 64. So this image encodes a lot more information than what our model was trained on. So we're going to have to change that shape to pass it through our model. And then we've got an image data type here, or tensor data type of torch uint8. So maybe that's going to be some errors for us later on. So if you want to go ahead and see if you can resize this tensor to 64, 64 using a torch transform or torch vision transform, I'd encourage you to try that out. And if you know how to change a torch tensor from uint8 to torch float32, give that a shot as well. So let's try and make a prediction on our image in the next video. I'll see you there. In the last video, we loaded in our own custom image and got 2 big thumbs up from my dad, and we turned it into a tensor. So we've got a custom image tensor here. It's quite big though, and we looked at a few things of what we have to do before we pass it through our model. So we need to make sure it's in the data type torch float32, shape 64, 64.3, and on the right device. So let's make another section here. We'll go 11.2, and we'll call it making a prediction on a custom image with a PyTorch model, or with a trained PyTorch model. And albeit our models aren't quite the level we would like them at yet, I think it's important just to see what it's like to make a prediction end-to-end on some custom data. Because that's the fun part, right? So try to make a prediction on an image. Now, I want to just highlight something about the importance of different data types and shapes and whatnot, and devices. 3 of the biggest errors in deep learning. Let's see what happens if we try to predict on uint8 format. So we'll go model1.eval, and with torch.inference mode, let's make a prediction. We'll pass it through our model 1. We could use model 0 if we wanted to here. They're both performing pretty poorly anyway. Let's send it to the device and see what happens. Oh no, what did we get wrong here? Runtime error, input type. So we've got uint8, So this is one of our first errors that we talked about. We need to make sure that our custom data is of the same data type that our model was originally trained on. So we've got torch CUDA float tensor. So we've got an issue here. We've got a uint8 image data or image tensor trying to be predicted on by a model with its data type of torch CUDA float tensor. So let's try fix this by load in the custom image and convert to torch.float32. So one of the ways we can do this is we'll just recreate the custom image tensor, and I'm going to use torchvision.io.readImage. We don't have to fully reload our image, but I'm going to do it anyway for completeness and a little bit of practice. And then I'm going to set the type here with the type method to torchFloat32. And then let's just see what happens. We'll go custom image. Let's see what this looks like. I wonder if our model will work on this. Let's just try again. We'll bring this up, copy this down to make a prediction, and custom image.toDevice. Our image is in torchFloat32 now. Let's see what happens. Oh, we get an issue. Oh my goodness, that's a big matrix. Now I have a feeling that that might be because our image, our custom image is of a shape that's far too large. Custom image.shape. What do we get? Oh my gosh, 4,000 and 3,024. And do you notice as well that our values here aren't between 0 and 1? Whereas our previous images, do we have an image? There we go. That our model was trained on were between 0 and 1. So how could we get these values to be between 0 and 1? Well, one of the ways to do so is by dividing by 255. Now, why would we divide by 255? Well, because that's a standard image format, is to store the image tensor values in values from 0 to 255 for red, green, and blue color channels. So if we want to scale them, so this is what I meant by 0 to 255, if we wanted to scale these values to be between 0 and 1, we can divide them by 255 because that is the maximum value that they can be. So let's see what happens if we do that. Okay, we get our image values between 0 and 1. Can we plot this image? So plt.imshow, let's plot our custom image. We got to permute it so it works nicely with matplotlib. What do we get here? Beautiful, we get the same image, right? But it's still quite big. Look at that. We've got a pixel height of, or image height of almost 4,000 pixels and a width of over 3,000 pixels. So we need to do some adjustments further on. So let's keep going. We've got custom image to device. We've got an error here. So this is a shape error. So what can we do to transform our image shape? And you might have already tried this. Well, let's create a transform pipeline to transform our image shape. So create transform pipeline or composition to resize the image. Because remember, what are we trying to do? We're trying to get our model to predict on the same type of data it was trained on. So let's go custom image transform is transforms.compose. And we're just going to, since our image is already of a tensor, let's do transforms.resize, and we'll set the size to the same shape that our model was trained on, or the same size that is. So let's go from torch vision. We don't have to rewrite this, it's already imported, but I just want to highlight that we're using the transforms package. We'll run that. There we go, we've got a transform pipeline. Now let's see what happens when we transform our target image. Transform target image, what happens? Custom image transformed. I love printing the inputs and outputs of our different pipelines here. So let's pass our custom image that we've just imported. So custom image transform. Our custom image is, recall, of shape, quite large. We're going to pass it through our transformation pipeline, and let's print out the shapes. Let's go original shape, and then we'll go custom image dot shape, and then we'll go print transformed shape, is going to be custom image underscore transformed dot shape. Let's see the transformation. Oh, would you look at that? How good. We've gone from quite a large image to a transformed image here. So it's going to be squished and squashed a little. So let's see what happens when we plot our transformed image. We've gone from 4,000 pixels on the height to 64, and we've gone from 3,000 pixels on the height to 64. So this is what our model is going to see. Let's go custom image transformed, and we're going to permute it to be 120. Okay, so quite pixelated. Do you see how this might affect the accuracy of our model? Because we've gone from custom image, is this going to, oh yeah, we need to plot.imshow. We've gone from this high definition image to an image that's of far lower quality here. And I can kind of see myself that this is still a pizza, but I know that it's a pizza. So just keep this in mind going forward, is that another way that we could potentially improve our model's performance if we increased the size of the training image data. So instead of 6464, we might want to upgrade our model's capability to deal with images that are of 224. So if we have a look at what this looks like, 224. Wow, that looks a lot better than 6464. So that's something that you might want to try out later on, but we're going to stick in line with the CNN explainer model. How about we try to make another prediction? So since we've transformed our image to be the same size as the data our model was trained on, so with torch inference mode, let's go custom image pred equals model1 on custom image underscore transformed. Does it work now? Oh my goodness, still not working. Expected all tensors on the same device. Of course, that's what we forgot here. Let's go to device. Or actually, let's leave that error there, and we'll just copy this code down here, and let's put this custom image transform back on the right device and see if we finally get a prediction to happen with our model. Oh, we still get an error. Oh my goodness, what's going on here? Oh, we need to add a batch size to it. So I'm just going to write up here, this will error, no batch size, and this will error, image not on right device. And then let's try again. We need to add a batch size to our image. So if we look at custom image transformed dot shape, recall that our images that pass through our model had a batch dimension. So this is another place where we get shape mismatch issues. Is if our model, because what's going on in a neural network is a lot of tensor manipulation, if the dimensions don't line up, we want to perform matrix multiplication, and the rules, if we don't play to the rules, the matrix multiplication will fail. So let's fix this by adding a batch dimension. So we can do this by going a custom image transformed. Let's unsqueeze it on the first dimension and then check the shape. There we go. We add a single batch. So that's what we want to do when we make a prediction on a single custom image. We want to pass it to our model as an image or a batch of one sample. So let's finally see if this will work. Let's just not comment what it will do. This, or maybe we'll try anyway. This should work. Added a batch size. So do you see the steps we've been through so far? I'm just going to unsqueeze this. Unsqueeze on the 0th dimension to add a batch size. Oh, it didn't error. Oh my goodness, it didn't error. Have a look at that. Yes, that's what we want. We get a prediction logit because the raw outputs of our model. We get a logit value for each of our custom classes. So this could be pizza, this could be steak, and this could be sushi, depending on the order of our classes. Let's just have a look. Class to IDX. Did we not get that? Class names. Beautiful. So pizza, steak, sushi. We've still got a ways to go to convert this into that, But I just want to highlight what we've done. So note, to make a prediction on a custom image, we had to, and this is something you'll have to keep in mind for almost all of your custom data. It needs to be formatted in the same way that your model was trained on. So we had to load the image and turn it into a tensor. We had to make sure the image was the same data type as the model. So that was torch float 32. And then we had to make sure the image was the same shape as the data the model was trained on, which was 64, 64, 3 with a batch size. So that was 1, 3, 64, 64. And excuse me, this should actually be the other way around. This should be color channels first because we're dealing with PyTorch here. 64. And then finally, we had to make sure the image was on the same device as our model. So they are three of the big ones that we've talked about so much. Same data type or data type mismatch will result in a bunch of issues. Shape mismatch will result in a bunch of issues. And device mismatch will also result in a bunch of issues. If you want these to be highlighted, they are in the learnpytorch.io resource. We have putting things together. Where do we have it? Oh yeah, no, it's in the main takeaway section, sorry. Predicting on your own custom data with a trained model is possible as long as you format the data into a similar format to what the model was trained on. So make sure you take care of the three big PyTorch and deep learning errors. Wrong data types, wrong data shapes, and wrong devices. Regardless of whether that's images or audio or text, these three will follow you around. So just keep them in mind. But now we've got some code to predict on custom images, but it's kind of all over the place. Like we've got about 10 coding cells here just to make a prediction on a custom image. How about we functionize this and see if it works on our pizza dad image. I'll see you in the next video. Welcome back. We're now well on our way to making custom predictions on our own custom image data. Let's keep pushing forward. In the last video, we finished off getting some raw model logits, so the raw outputs from our model. Now, let's see how we can convert these logits into prediction labels. Let's write some code. So convert logits to prediction labels, or let's go convert logits. Let's first convert them to prediction probabilities. So how do we do that? Let's go custom image pred probs equals torch.softmax to convert our custom image pred across the first dimension. So the first dimension of this tensor will be the inner brackets, of course. So just this little section here. Let's see what these look like. This will be prediction probabilities. Wonderful. So you'll notice that these are quite spread out. Now, this is not ideal. Ideally, we'd like our model to assign a fairly large prediction probability to the target class, the right target class, that is. However, since our model, when we trained it, isn't actually performing all that well, the prediction probabilities are quite spread out across all of the classes. But nonetheless, we're just highlighting what it's like to predict on custom data. So now let's convert the prediction probabilities to prediction labels. Now you'll notice that we used softmax because why? We are working with multi-class classification data. And so we can get the custom image pred labels, or the integers, by taking the argmax of the prediction probabilities. Custom image pred probs across the first dimension as well. So let's go custom image pred labels. Let's see what they look like. 0. So the index here with the highest value is index number 0. And you'll notice that it's still on the CUDA device. So what would happen if we tried to index on our class names with the custom image pred labels? Or maybe that doesn't need to be a plural. Oh, there we go. We get pizza. But You might also have to change this to the CPU later on, otherwise you might run into some errors. So just beware of that. So you notice how we just put it to the CPU. So we get pizza, we got a correct prediction, but this is as good as guessing in my opinion, because these are kind of spread out. Ideally, this value would be higher, maybe something like 0.8 or above for our pizza dad image. But nonetheless, our model is getting 2 thumbs up, even on this 64 by 64 image. But that's a lot of code that we've written. Let's functionize it. So we can just pass in a file path and get a custom prediction from it. So putting custom image prediction together, let's go building a function. So we want the ideal outcome is, let's plot our image as well. Ideal outcome is a function where we plot or where we pass an image path to and have our model predict on that image and plot the image plus the prediction. So this is our ideal outcome, and I think I'm going to issue this as a challenge. So give that a go, put all of our code above together, and you'll just have to import the image, you'll have to process it and whatnot. I know I said we were going to build a function in this video, but we're going to save that to the next video. I'd like you to give that a go. So start from way back up here, import the image via Torch Vision IO read image, format it using what we've done, change the data type, change the shape, change the device, and then plot the image with its prediction as the title. So give that a go, and we'll do it together in the next video. How'd you go? I just realized I had a typo in the previous cell, but that's all right. Did you give it a shot? Did you put together the custom image prediction in a function format? I'd love it if you did, but if not, that's okay. Let's keep going. Let's see what that might look like. And there are many different ways that you could do this, but here's one of the ways that I've thought of. So we want a function that's going to pred and plot a target image. We want it to take in a torch model. And so that's going to be ideally a trained model. We want it to also take in an image path, which will be of a string. It can take in a class names list so that we can index it and get the prediction label in string format. So let's put this as a list of strings. And by default, this can equal none, just in case we just wanted the prediction. It wants to take in a transform so that we can pass it in some form of transform to transform the image. And then it's going to take in a device, which will be by default the target device. So let's write a little doc string here. Makes a prediction on a target image with a trained model and plots the image and prediction. Beautiful. Now, what do we have to do first? Let's load in the image. Load in the image just like we did before with Torch Vision. So target image equals torchvision.io.read image, and we'll go string on the image path, which will be the image path here, and we'll convert it to a string just in case it doesn't get passed in as a string. And then let's change it into type torch float 32, because we want to make sure that our custom image or our custom data is in the same type as what we trained our model on. So now let's divide the image pixel values by 255 to get them between 0 or to get them between 0, 1 as a range. So we can just do this by target image equals target image divided by 255. And we could also just do this in one step up here, 255, but I've just put it out there just to let you know that, hey, read image imports image data as between 0 and 255. So our model prefers numbers between 0 and 1, so let's just scale it there. Now, we want to transform our data if necessary. In our case, it is, but it won't always be. So we want this function to be pretty generic, pred and plot image. So if the transform exists, let's set the target image to the transform, or we'll pass it through the transform, that is. Wonderful, and the transform we're going to get from here. Now what's left to do? Well, let's make sure the model is on the target device. It might be by default, but if we're passing in a device parameter, we may as well make sure the model is there too. And now we can make a prediction. So let's turn on eval/inference mode and make a prediction with our model. So model, we'll call eval mode, and then with torch.inference mode, because we're making a prediction, we want to turn our model into inference mode or put it in inference mode context. Let's add an extra dimension to the image. Let's go target image. We could do this step above actually, but we're just going to do it here. I'm kind of remembering things on the fly here of what we need to do. We're adding let's write this down. This is the batch dimension, e.g. our model will predict on batches of 1x image. So we're just unsqueezing it to add an extra dimension at the 0th dimension space, just like we did in a previous video. Now let's make a prediction on the image with an extra dimension. Otherwise, if we don't have that extra dimension, we saw that we get a shape issue. So right down here, target image pred, and remember this is going to be the raw model outputs, raw logit outputs. We'll go target image pred, and yeah, I believe that's all we need for the prediction. Oh wait, there was one more thing. To device. Need to also make sure the target image is on the right device. Beautiful. So a fair few steps here, but nothing we can't handle. All we're really doing is replicating what we've done for batches of images, but we want to make sure that if someone passed any image to our pred and plot image function, that we've got functionality in here to handle that image. And do we get this? Oh, we want just target image to device. Did you catch that error? So let's keep going. Now let's convert the logits. Our model's raw logits. Let's convert those to prediction probabilities. This is so exciting. We're getting so close to making a function to predict on custom data. So we'll set this to target image pred probs, which is going to be torch.softmax. And we will pass in the target image pred here. We want to get the softmax of the first dimension. Now let's convert our prediction probabilities, which is what we get in the line above. We want to convert those to prediction labels. So let's get the target image pred labels equals torch.argmax. We want to get the argmax of, or in other words, the index, which is the maximum value from the pred probs of the first dimension as well. Now, what should we return here? Well, we don't really need to return anything. We want to create a plot. So let's plot the image alongside the prediction and prediction probability. Beautiful. So plot.imshow, what are we going to pass in here? We're going to pass in here our target image. Now we have to squeeze this, I believe, because we've added an extra dimension up here. So we'll squeeze it to remove that batch size. And then we still have to permute it because matplotlib likes images in the format color channels last, 1 to 0. So remove batch dimension and rearrange shape to be HWC, that is, color channels last. Now, if the class names parameter exists, so we've passed in a list of class names, this function is really just replicating everything we've done in the past 10 cells, by the way. So right back up here, we're replicating all of this stuff in one function. So pretty large function, but once we've written it, we can pass in our images as much as we like. So if class names exist, let's set the title to showcase that class name. So the pred is going to be class names. Let's index on that, pred image or target image pred label. And this is where we'll have to put it to the CPU, because if we're using a title with matplotlib, matplotlib cannot handle things that are on the GPU. This is why we have to put it to the CPU. And then I believe that should be enough for that. Let's add a little line in here so that we can have it, oh, I've missed something, an outside bracket there. Wonderful. let's add the prediction probability because that's always fun to see. So we want target image pred probs, and we want to get the maximum pred prob from that, and we'll also put that on the CPU. And I think we might get this to 3 decimal places. Now this is saying, oh, pred labels, we don't need that. We need just non-plural. Beautiful. Now, if the class names doesn't exist, let's just set the title equal to f string. We'll go pred target image pred label. Is Google Colab still telling me this is wrong? Target image pred label. Oh no, we've still got the same thing. It just hasn't caught up with me yet. I'm coding a bit fast here. And then we'll pass in the prob, which will be just the same as above. I could even copy this in. Beautiful. And let's now set the title to the title, and we will turn the axes off. PLT axes false. Fair bit of code there, but this is going to be a super exciting moment. Let's see what this looks like when we pass it in a target image and a target model, some class names, and a transform. Are you ready? We've got our transform ready, by the way. It's back up here. Custom image transform. It's just going to resize our image. So let's see. Oh, this file was updated remotely or in another tab. Sometimes this happens, and usually Google Colab sorts itself out, but that's all right. Doesn't affect our code for now. Pred on our custom image. Are you ready? Save failed. Would you like to override? Yes, I would. So you might see that in Google Colab. Usually it fixes itself. There we go. Save successfully. Pred and plot image. I was going to say, Google Colab, don't fail me now. We're about to predict on our own custom data using a model trained on our own custom data. Image path, let's pass in custom image path, which is going to be the path to our pizza dad image. Let's go class names equals class names, which is pizza, steak, and sushi. We'll pass in our transform to convert our image to the right shape and size. Custom image transform. And then finally, the target device is going to be device. Are you ready? Let's make a prediction on custom data, one of my favorite things, one of the most fun things to do when building deep learning models. 3, 2, 1. How did it go? Oh no, what did we get wrong? CPU. Okay, so close, but yet so far. Has no attribute CPU. Oh, maybe we need to put this to CPU. That's where I got the square bracket wrong. So that's what we needed to change. We needed to, because this is going to be potentially on the GPU, target image pred label, we need to put it on the CPU. We need to do that. Why? Because this is going to be the title of our matplotlib plot, and matplotlib doesn't interface too well with data on a GPU. Let's try it again. 3, 2, 1, running. Woohoo! Look at that. Prediction on a custom image, and it gets it right. 2 thumbs up. I didn't plan this. Our model is performing actually quite poorly, so this is as good as a guess to me. You might want to try this on your own image, and in fact, if you do, please share it with me. I would love to see it. But you could potentially try this with another model, see what happens. Steak. Okay, there we go. So even though model 1 performs worse quantitatively, it performs better qualitatively. So that's the power of visualize, visualize, visualize. And if we use model 0, also which isn't performing too well, it gets it wrong with a prediction probability of 0.368, which isn't too high either. So we've talked about a couple of different ways to improve our models. Now we've even got a way to make predictions on our own custom images. So give that a shot. I'd love to see your custom predictions. Upload an image here if you want, or download it into Google Colab using code that we've used before. But we've come a fairly long way. I feel like we've covered enough for custom data sets. Let's summarize what we've covered in the next video. And I've got a bunch of exercises and extra curriculum for you. So this is exciting stuff. I'll see you in the next video. In the last video, we did the very exciting thing of making a prediction on our own custom image. Although it's quite pixelated, and although our model's performance quantitatively didn't turn out to be too good, qualitatively, it happened to work out. But of course, there are a fair few ways that we could improve our model's performance. But the main takeaway here is that we had to do a bunch of pre-processing to make sure our custom image was in the same format as what our model expected. And this is quite a lot of what I do behind the scenes for Nutrify. If you upload an image here, it gets pre-processed in a similar way to go through an image classification model to output a label like this. So let's get out of this. To summarize, I've got a colorful slide here, but we've already covered this. Predicting on custom data. These are 3 things to make sure of, regardless of whether you're using images, text, or audio. Make sure your data is in the right data type. In our case, it was torch float 32. Make sure your data is on the same device as the model. So we had to put our custom image to the GPU, which was where our model also lived. And then we had to make sure our data was in the correct shape. So the original shape was 64:64:3. Actually, this should be reversed because it was color channels first, but the same principle remains here. We had to add a batch dimension and rearrange if we needed. So in our case, we used images of this shape, batches first, color channels first, height, width. But depending on your problem will depend on your shape, depending on the device you're using will depend on where your data and your model lives, and depending on the data type you're using will depend on what you're using for torch float 32 or something else. So let's summarize. If we go here, main takeaways, you can read through these, but some of the big ones are PyTorch has many built-in functions to deal with all kinds of data, from vision to text to audio to recommendation systems. So if we look at the PyTorch docs, you're going to become very familiar with these over time. We've got torch audio data, torch text, torch vision is what we practiced with. And we've got a whole bunch of things here for transforming and augmenting images, datasets, utilities, operators, and torch data is currently in beta, but this is just something to be aware of later on. So it's a prototype library right now, but by the time you watch this, it might be available. But it's another way of loading data. So just be aware of this for later on. And if we come back to up here, if PyTorch built-in data loading functions don't suit your requirements, you can write your own custom dataset classes by subclassing torch.utils.data.dataset. And we saw that way back up here in option number 2. Option 2, here we go. Loading image data with a custom dataset. We wrote plenty of code to do that. And then a lot of machine learning is dealing with the balance between overfitting and underfitting. We've got a whole section in the book here to check out what an ideal loss curve should look like and how to deal with overfitting, how to deal with underfitting. It is a fine line. So much of the research in machine learning is actually dedicated towards this balance. And then 3 big things for being aware of when you're predicting on your own custom data: wrong data types, wrong data shapes, and wrong devices. This will follow you around, as I said, and we saw that in practice to get our own custom image ready for a trained model. Now, we have some exercises here. If you'd like the link to it, you can go to learnpytorch.io, section number 4, exercises, and of course, extra curriculum. A lot of the things I've mentioned throughout the course that'd be a good resource to check out contained in here. But the exercises, this is your time to shine, your time to practice. Let's go back to this notebook. Scroll right down to the bottom. Look how much code we've written. Goodness me. Exercises. For all exercises and extra curriculum, see here. Turn that into Markdown. Wonderful. And so if we go in here, you've got a couple of resources. There's an exercise template notebook for number 4 and example solutions for notebook number 4, which is what we're working on now. So of course, I'd encourage you to go through the PyTorch custom datasets exercises template first. Try to fill out all of the code here on your own. So we've got some questions here, we've got some dummy code, we've got some comments. So give that a go. Go through this, use this book resource to reference, use all the code we've written, use the documentation, whatever you want, but try to go through this on your own. And then if you get stuck somewhere, you can look at an example solution that I created, which is here. PyTorch custom datasets exercise solutions, and just be aware that this is just one way of doing things. It's not necessarily the best, it's just a way to reference what you're writing to what I would do. And there's actually now live walkthroughs of the solutions, errors and all, on YouTube. So if you go to this video, I'm just going to mute. So this is me live streaming the whole thing, writing a bunch of PyTorch code. If you just keep going through all of that, you'll see me writing all of the solutions, running into errors, trying different things, etc., etc. But that's on YouTube. You can check that out on your own time. But I feel like we've covered enough. Exercises. Oh, by the way, this is in the extras, exercises tab of the PyTorch Deep Learning repo. So extras, exercises and solutions are contained in there. Far out. We've covered a lot. Look at all that. So that has been PyTorch Custom Datasets. I will see you in the next section. Holy smokes. That was a lot of PyTorch code. But if you're still hungry for more, there is 5 more chapters available at learnpytorch.io, which cover transfer learning, my favorite topic, PyTorch model experiment tracking, PyTorch paper replicating, and PyTorch model deployment. How do you get your model into the hands of others? And if you like to learn in this video style, the videos for those chapters are available at zerotomastery.io. But otherwise, happy machine learning, and I'll see you next time.